L2.1 approach.
Let's see here. All right, good. People can hear me? Yes, I see level. Hopefully everyone can hear me. We'll get started. We got a lot of stuff to go through today. I just answered Zach's question, kind of. But we'll be talking more about that. Going over today, I know the reading was probably pretty intense. This chapter 5 stuff's all the aerodynamics things, and they like to cover a lot. They crammed a lot into that chapter, that's for sure. I'm going to try to go through all that material, also flight controls today and airplane systems. That was the plan, but obviously if we need to spend more time on the aerodynamic stuff, I'd rather do that. It's really important to cover that and understand that really well. All right, awesome. And everyone knows how to use the thread for questions out there. I hope this time you can find the thread. I have it in the window today, so you'll see the questions streaming over there on the right side. Yeah. So just don't spam the thread, please. With
We're looking at you, Brian.
yeah, or Ryan too. Yeah, both of you guys. All right, well, let's.
We haven't done anything yet.
Yeah, now they're like, all right, we have our own billboard. We can
Lay down that gauntlet.
Yeah, oh my gosh. Yeah, anyhow. Yeah, if you have your phones, just make sure they're on whatever, and then hopefully that phone doesn't go off. So let's get going. Reading was chapters 4, 5, and 6. 6 was pretty lightweight compared to 5, so it was probably a relief when you got to that one. Aerodynamics, loading and forces, flight controls, and then aircraft systems. Now, aircraft systems is chapter 7. That's also a very long chapter, so I wanted to make sure if we had time we could start on that today. So also understanding how long 5 was, I went through and kind of pulled out some sections of chapter 7 that aren't applicable to the private ground. So that should lighten the reading responsibility on that chapter. So first, I'd just like to recap what we talked about in week 1. So we went over PAVE. We talked about aeronautical decision making. PAVE was one of the aspects. This one comes up often in flight training. Again, it's looking at the pilot, yourself, the pilot, the aircraft, the environment. The V is the environment, and external pressures. So pilot, am I in a good condition to, am I healthy enough to fly? Do I understand this aircraft well enough to fly it? Would I pass a medical in the condition I'm in? The aircraft, knowing the aircraft equipment, are you proficient in it? Can the aircraft actually do the mission? Can it carry these 4 passengers in a full load and go the whole route? Is the aircraft legal? Has it had its annual, all the maintenance requirements? Is there a airworthiness directive that's been complied with? Do I need to get a waiver? Environment, obviously the weather, the route, the airports, knowing and understanding how to get around the airports. Does the airport have the facilities that you need to actually do your flight? And then external pressures is obviously wanting to perform for somebody, to get there on time, to be at a party. A lot of things can be external pressures. Even you have a meeting or a business deal that you're trying to get to and you're flying yourself to, and you don't want to not be there in person. So a lot of things can solve up to that. And then we looked at this graph, which is, looking at risk assessing a flight, and then looking at your capabilities and the requirements of that. And if you go into the red zone, then you've basically outdone you don't have the capabilities to perform the mission. Also talk about airworthiness standards. Airframe, engines, propellers all have log books, have required maintenance on them. And then the aircraft is issued that airworthiness certificate when it's approved. So the certificate's always valid with the plane, but airworthiness directives can render a plane not airworthy unless they're complied with, and also annual maintenance requirements. As a point of interest, I just saw this email from the FAA this week about a DA-40 fuel hose deterioration, prompting an airworthiness directive. And I flew DA-40s in the flying club. So I'm familiar with this plane, and there's a lot of them out there. Coincidentally, 737 of them. I thought that 737. Diamond DA-40s. It's kind of funny. Yes, so there was also one just below with the Kodiak. These ones, I mean, I happen to see through AOPA, but I actually did see this on the FAA. There's an FAA thread that you can subscribe to anytime there's an AD. But this one also actually popped up on AOPA because it is a pretty popular aircraft for training. Some of the key flight terminology which will be important today as well. A force. Force will accelerate an object in the direction or the vector it's applied. It will accelerate an object. It has nothing to do with the actual speed of the object, and that's really, really important because the FAA will try to trick you on this. They will tell you, they'll say, oh, there's these forces, and so the plane's not moving, right, if the forces are equal. But that's not true. If the forces are equal and the plane's already in motion, it's just not going to change in velocity. So it either remains still or it'll continue moving at whatever rate it's moving. And that's a really important distinction to keep in mind. So the four named forces we know are thrust, drag, lift, and weight. You probably had that railed into your head while you were reading through chapter 5. The center of gravity is, again, this imaginary point on the plane that if you were to hang the plane, it would balance on it. And any action, any arm moment around the center of gravity is around the center of gravity. So if you were to take the tail of the aircraft and push on it, it's going to rotate around that center of gravity point. If you push on the wing, it's going to rotate around the center of gravity point. And that's going to be important when we start talking about stability in today's class. Center of lift is just another force that's exerting in flight, and that is, it's pretty much going to be at the same place on the top of the wing. So the center of gravity will move around that, and it's another moment. So if you imagine two strings pulling on a board, the center of gravity is pulling one way and the center of lift's pulling another way. And that tail out there is kind of offsetting that difference so that when you're in level flight, the tail is really the one that's keeping you from, not flipping around. That when we talk about the forces and stability, again, that'll be something that'll come up. The motions, just pitching, rolling, sometimes banking, and yaw. Again, those are all through the center of gravity. Those are along the axes, the vertical, lateral, longitudinal axis. I hope I did the lines correctly. Yeah, so here we go. Thrust, drag, lift, weight. Lift, pulling the plane up. Thrust, pulling the plane forward. Drag, pulling it opposite of thrust, generally speaking, and weight, pulling opposite to lift. And then the axes with those three motion descriptions. Talked about aircraft components. Simple stuff, but power plant includes the engine and the propeller. That's kind of the important. The fuselage, again, obvious thing, but wings, ailerons, flaps, winglets, fuel tanks, it's all providing lift and controlling the rolling. Empennage, horizontal, vertical stabilizer, VTAILs and T-tails will actually talk a little bit about those today in stability. Rudder, elevator, trim, and stabulator. I always want to say stabilitator. I don't know why. And sometimes there's antennas attached to it. It controls pitch and yaw. Landing gears, the important things about that is it supports the plane on the ground as well when you're taxiing around, and obviously it keeps you from dinging the prop and the tail. So it's good to know that your landing gear's in good shape, even on the ground. So one of the things I saw while going through the written test is they want you to know what the slotted flap is and why is it different and what's special about it. So there's some questions on the written about slotted flap. Actually, we'll talk about that particular flap type today too. Mentioned air and airfoil. So air is necessary to generate lift. The wing is pushing on the air, pushes back. We also talked about Bernoulli sucking the plane up. Air is also necessary to generate thrust. We'll talk a lot more about these aspects today. This is sort of the introduction thing. Did it help you guys to actually have a little bit of that before going into chapter 5 last week? I hope so. Made it a little bit easier. Air's viscosity, slow plane down, causing drag. I talked a little bit about parasite drag and a little bit about induced drag from air. And again, density is the amount of air particles in a fixed volume. So as the density of air changes, so does its effect on lift and drag. There was formulas, if you guys looked at the formulas in chapter 5. But if you notice, the lift and drag formulas are almost identical except for the coefficient of lift and the coefficient of drag. And the components of it were air density, velocity, again, wing surface area and that. But mostly we'll be looking at air density and velocity, looking at those equations. Bernoulli, again, that's that pressure difference between the low side and the high side, and that's like the drinking straws drawing the wing up. And I say in normal flight here, the air on top of the wing is going to be lower pressure than below. And in that configuration, the air is flowing faster, so it has a reduced density, reduced pressure, and that's what pulls it up. And then we talked about the wind going around the wingtips, and that's inducing drag. And there was things in the new chapter about downwash and that wingtip vortices. And the funny thing about the FA is it mixes the terms up, if you notice that. It's like, oh, it's downwash, but it's wingtip vortices, but it's also induced drag. It's like, well, are they different things, or are they all the same thing? And I just kind of concluded they're all induced drags, forms of induced drag. This can be massive. There was a section in 5 that talked about how large aircraft can really create these huge vortices and how to stay clear of them. This picture was in that chapter. We didn't talk about this last week, but this is how basically Bernoulli proved this idea with this Venturi tube. Is it Bernoulli or Venturi? I don't know why Venturi doesn't get any credit for any of this. It's all Bernoulli, but the pressure is reduced. So do you guys understand that the volume of air coming in this diagram and going out is the same? The rate and the volume of the air coming in and going out. So the idea here is think about the number of particles of air that are passing any of those sampling points, those 3 sampling points. So if you were to say how much air is passing through this point, it's going to be the same. It has to be the same, right? So, the reason it speeds up in the middle, not the reason, but as a consequence of that, they are speeding up in the middle because it's trying to pass through the same number of air particles, at that moment. So the only way that the pressure coming into that and going out of that can be the same as if in that middle, in that constriction, there's the speed is going fast enough to be consistent at the output and provide it. There's limitations at some point. If it gets too narrow, it does some other things.
I think it's easier to wrap your mind around if you picture that it speeds up again or slows down again as it comes in.
Right.
Then you understand the volumes are the same. If it goes in at one volume, comes out at the same, then the speed going through the middle makes more sense.
Yep.
If you picture the slowing down part before it comes out of the Venturi.
Yeah, it has to. It's basically the amount of air passing at any point, the amount of air. It has to go fast in order for the same number of bits of air to pass that point.
Balloon.
Yeah.
Around the room.
Okay, so that was kind of the recap. And so now we'll start on the rest of this aerodynamic stuff. So one of the first images we saw in that, part of that chapter 4 thing was talking about the shape of the airfoil. And the key concept here is the chord line, the line that's drawn from the leading edge to the trailing edge through the wing. There's also the camber, but the camber is what actually helps control that pressure differential. So this is more of a terminology thing. Understanding what the chord line is important when we start talking about angle of attack. Because angle of attack is the relative wind, angle from the relative wind and that chord line. So that chord line will be mentioned over and over again when we talk about angle of attack. So again, angle of attack is the angle between the chord line and the relative wind. And it applies to all airfoils. So a propeller, the wing, a horizontal stabilizer, a vertical stabilizer, all of those components, a canard or whatever, it's that thing on the front of the airplane. But all of these are airfoils, and angle of attack applies to all of these. The important thing is that for each of those each angle of attack, there's an airspeed that will maintain altitude, and that's in steady unaccelerated flight. Again, the forces are balanced. So there's an angle of attack that if you have, that'll maintain the aircraft in that. Now, if you exceed the critical angle of attack, lift goes away and there's nothing that's going to maintain the flight. So here's this diagram that was in the book just showing flight path relative wind. And it's showing you the chord line and then the angle of that chord line against the relative wind, and that's the angle of attack. So as thrust is reduced and airspeed decreases, what has to happen is the angle of attack has to be increased to generate the same amount of lift, right, to maintain altitude, to balance that lift and weight. So if weight is increased, then the angle of attack must also be increased because it has to overcome that weight, right? So if the weight goes up too much, you're going to eventually get to an angle of attack that's the critical angle of attack, right? So, and then the wing stalls. The critical angle of attack does not depend on weight or airspeed. Well, that sounds really confusing because I just said, you know, if the weight increases, you have to increase the angle of attack. I'm talking about the critical angle of attack. This is the angle of attack where the wing no longer produces lift, right? It's that angle between the relative wind and the chord line. And that's not going to matter on weight. I mean, you're going to have to increase the angle of attack because of weight, but that's not really changing the critical angle of attack, right? It's you're changing the angle. The wing has to take a bite of air in order to overcome weight, but that's not changing the critical angle of attack. I know I'm trying to say this like a bunch of different ways, but it's a hugely confusing thing that people, you know, swap the idea of, oh, so well, the angle of attack has to do with weight, and it's not. It has to do with the design of the wing, and the wing is designed such that a certain angle of attack, it stops producing lift. So again, say it again. Angle of attack is the chord line and the relative wind at any airspeed, So just because you have to generate more lift because your weight's increased, you're gonna have to choose a different angle of attack that generates more lift. But that's the difference between the chord line and the relative wind at any airspeed. Guys in here, that's cool. I'll move on, or is that pretty clear? Did everyone get that? All right.
Find out when we get up.
Again, think of that drawing there on the top, right? And then think about that chord line and the relative wind. So I mentioned earlier the lift and the drag formulas almost look identical, except they have different coefficient of lift and coefficient of drag values. The coefficient of lift and the coefficient of drag is a different value depending on the angle of attack. So they measure the aircraft in the different angles of attack, and then capture this value, and then they can generate a table out of it. So you can see by the equation. Well, we said before, lift can be changed by altering the angle of attack of the wing. So again, that coefficient of lift is going to depend on that angle of attack. So that'll tell you how much lift you're going to get from that. And I said that each angle of attack has a coefficient of lift, coefficient of drag. And the two formulas, like I said, have a lot in common. So you can see that they depend on air density and the velocity squared, surface area of the wing. You can't do much about that, but you can change it if you put flaps out, right? Or you can change the camber of the wing by tipping in the aileron up or down. So you can change that value in flight because you're changing one of the surfaces of the wing. But assuming you're not doing that, the surface is the same size. It's what you think about when you look at these tables. Yes. So what you can tell by the formulas is because both of them depend on the same values, increasing air density or velocity is going to increase drag. And same thing for lift. It's going to increase lift, but it's going to be at different rates depending on the coefficient of lift and the coefficient of drag at the particular angle of attack. And I think this will make more sense when we look at that table. Because the formulas are so similar, and and believe me, there's probably additional details of this formula that they simply removed because it's not just this. These are the biggest factors that affect it, right? So if you were to divide the two formulas out, what do you end up with is like lift over drag. You end up with a ratio of the two, and that's how they like to look at it when we look at where's our most efficient performance. What's our angle of attack that gives us the most efficient performance of lift over drag? So they take measurements. So you can see the orange line here is the, let's see if I can do the fancy pen thing today. I don't know. Is it doing anything? Does it show anything? Nothing. It's just advancing the slide. That's great.
It did for a second.
There was a little doodad?
Yeah.
Okay. Yeah. Okay. So if you can see here this orange line, that's the measurement of the coefficient of drag at these different angles of attack, right? So they measure that, and then they measure this coefficient of lift. And then as you can see at some point, and usually it's normally like this, somewhere between 16 and 20, that the lift just completely goes away. So you can imagine a wing is like this, and eventually there's no airflow over the top. So it's generating lift, but it's not generating enough to even be meaningful at that point. Still generating lift, right, after CL max. You can see the red line continues, but it rapidly drops off. And then you're seeing that the coefficient of drag is going up super, super fast right there. And it comes up so fast at that point, doesn't make any sense to even look at the lift at that point. So we see this, this green line. So what they do is they take those two formulas and divide them, and then you end up with this ratio, right? So now you can see there's this sweet spot at about 6 degrees that lift and drag is, the relationship is at the max. So that means you're going to get your maximum benefit. And this is generally what we call your best glide speed. And it's something that's typically published in your owner's handbook. It'll tell you, like in our Saratoga, it's 83 knots. But in a 172, it might be 67 knots or something like that. And this is what's going to, if your engine dies, this is the speed you want to fly because it's going to get you the furthest distance, right? So your lift and your drag are at the ideal optimal values at that point. So when you see this table, this will be in the written test. They'll have this table and they'll ask questions basically around the things I just pointed out. You know, what's the benefit of that lift drag ratio max there? Guys in the room or online, if you have any questions about this table. No. Online too. I know it's a little delayed. You guys get the video about 30 seconds after I say it, but I can certainly go back. So we mentioned that velocity and air density are both factors on lift and drag. And I think I mentioned last week about air density. When it's hotter, the air is less dense. When it's colder, it's more dense. At higher elevations, it's less dense. So you can see its effect on these equations. Again, coefficient of lift and drag operate at different rates. So the altitude, it's not going to be the same, effect, but there's definitely an effect. At a high altitude, you get less drag, but you also get less lift. And then air density is also affected by moisture. So if the air is more moist, it's less dense because water does not generate lift. Water just takes the place of air.
More thrust.
What's that?
More thrust.
So no, thrust affects this too because the propeller is an airfoil, and these are airfoil formulas. So the propeller is subject to the same lift and drag issues here. In the effectiveness of the elevator and everything is affected in this case. So you can see that if you increase the velocity, you're going to get more lift, but you're also going to get more drag. And then, induced drag there's the two types, right? The parasite drag. So the parasite drag is really what keeps you from going faster and faster and faster, kind of. Like the faster you go, the more the little air bits are holding on to the rough surfaces and the things sticking out of your plane, right? And you get to a certain point where you just can't go any faster. Another way to think about this is if you know about parachuting, right? There's a terminal velocity, right? You're falling out of the sky, but there's this point where you get to where you stop falling faster, right? Because that air that's rushing up you is the force that's keeping you from accelerating. So you're balanced. Your forces are balanced, right? Gravity is pulling you down at one force, and your own drag is pulling you up in the other way, right?
For a minute.
Well, that's terminal velocity, and as long as you don't hit the ground, you're going to have terminal velocity, yeah.
Brian had a question.
Let's see here. Ooh, this is relative to the wind. So if you're climbing fast enough at why is this off the screen? Let me see if I can pull this over. Yeah, a pitch of 25 degrees. Yeah, so your pitch to your climb, yeah, isn't necessarily, yeah, the pitch of your climb isn't. Once you, yeah, and we'll talk about this later. So once you've established the climb, your relative wind is practically the same as it is in level flight. And that's kind of weird to think about it that way, but we'll actually talk about that in a later slide. So yeah, the pitch relative to the ground, it doesn't really have anything to do with the relative wind when you're in a climb, right? Because that's your wing is faced to how the wind's coming over the wing. Yep.
The whole point of this is kind of that even though your plane's pointed this direction, you could still be moving this direction. That's, I mean.
Yeah, I mean, if you're using lift to counteract weight, right? Your plane is so heavy. This is the only angle of attack that you can. This is the angle of attack you need to maintain level of flight. If you were to increase that angle of attack, you might start climbing.
Right.
But once you establish the climb, your angle of attack is going to be roughly the same. Although you need additional thrust to overcome drag. And again, I'll get to that though. There's a slide where we talk about that. Yeah.
That's an exaggeration, but the whole point of the angle of attack is you're flying this way, but you might have to turn the plane this way to keep going straight, right?
Yeah, if your weight increases or the air density changes, you might need a greater angle of attack. And
Slower.
yep, yeah, if you're going slower because it's a function of velocity, yeah, you might have to increase the angle of attack in order to maintain lift. Or the way drag changes at different airspeeds, right? So if your drag becomes more, you're going to need more lift. You're going to have to find some combination of balancing those two so you don't descend. Okay, so that's velocity and air density. I actually have, it's not on here, okay. Yeah, I have some demonstrations. I have paper cutouts. This will be fun. So let's see if I can switch from the presentation over to the table. Is the camera not on? It will go on fast. There we go. Yes. Okay, so I did some little things here. What I got here is, this is air density. That's what this is representing. So this is, let's say this is standard, and this is hot air. So you see how the holes, this is the air density, the holes are wider apart. And then here's cold air, right, on the bottom. So let's say in order to take this plane off, we just have to pass so many bits of air, right? And then if we do that, we can take off the ground if you're just counting bits of air. So obviously with the cold air, we're going to pass a lot of bits of air, and then we're going to take off like really quick. In a standard, we might have to go a little bit further, and then we'll take off. This is just another way to look at it, right? In hot air, we're obviously going to have to go further, right? And we have to go faster. So we have to increase velocity, right, to make up for that air density, basically it. So you can see if you're in really hot weather, you're going to come here and you might not take off, right? Yep. And this also, this can be either hot or this can be at a high altitude. So think of a hot day at a high elevation, how much runway you're going to need to take off, because you're not getting enough air passing over the wing. You have to increase velocity, but if you increase velocity, you're passing over the ground at a faster rate. So that
Humid too, right?
Humid, and that's what this guy is. So let's say this is your standard air, but let's throw some moisture in it. Make sure I got these lined up right. Yeah. So you can see now, there's the moisture taking the place of restrict the air in those spots. So now you need, and it's not as great of an effect as hot air. Moisture will have an effect. And that's what I was mentioning in Slack, is there was an article that AOPA did analyzing, like, okay, how much does humidity really affect it, and should we be a little more serious about it? Because normally we don't even look at it when we do these calculations. But you can see here, with those bits of water taking place of air, we're going to need longer, right? We're going to need to go faster, use up more runway. And the other side to this, and we haven't talked about airspeed indicators, but the airspeed indicator is actually measuring the counts of bits of air in one way. It's ram air that's getting shoved into this tube. And so when the air gets pushed into this tube, there's a pressure from that air, and then there's the static pressure outside, and it looks at the difference. So in a sense, the airspeed indicator is really measuring bits of air that are going over your wing. So it's going to indicate an airspeed. It's not your ground speed, and it's important to know. Why the airspeed indicator is so important is because it's actually indicating airflow over your wing. It's not telling you how fast you're going. It's telling you how much airflow is going over your wing. And when you look at stall tables and things like that, it's talking about indicated airspeed or sometimes calibrated airspeed, which are usually pretty close together. When they can be affected by humidity and things like that. But that's why indicated airspeed doesn't really tell you how fast you're going over the ground. But it does tell you, it critically tells you how much airflow is going over your wing. So imagine you're going down the runway, right? And those different rotation points, what are you going to see in the cockpit when you rotate? You're seeing the exact same airspeed each time. Is that trippy or what? But you're going to be taking off at way different locations down the runway. So that's why air density is hugely important. Yeah. So to summarize, the tiny bits of air passing over an airfoil, that's your airspeed indicator. Your takeoff distance, the speed required to generate enough lift, right? And that lift equation depends on air density and velocity.
It's accurate to say that the airspeed indicator actually also indicates or measures air density then?
I mean, you would have to derive it, but I mean, it's measuring how dense. Yeah, it's
not a number that you can use, but
yeah.
The air density is going to change the airspeed indicator.
Yes. Well, it's not changing the airspeed indicator. It's just it's a reflection of how much air is passing over the wing, and as the air is less dense, right, your airspeed will indicate according to that.
Your actual speed increases in order to get enough air to indicate the airspeed.
So when you land at a high altitude airport on a hot day, your ground speed is going to be faster than the same airport at a lower altitude. Right. So you're going to actually need a longer distance to roll out. And that's why the tables say, what's your altitude? And they have density altitude tables. What's your deviation from standard? And this is how much extra you have to add to your landing or your takeoff distance. And if you're going to clear an obstacle, your lift to get over an obstacle is going to be reduced too. So you're going to need a greater distance to clear things. So. Perfect example, Big Bear in the summer in a 172 with 2 passengers and full fuel. You'll climb at like 200 feet a minute. You take that same airplane and put it in Santa Maria at 60 degrees and you'll climb at 700 feet a minute. So, yeah. So yeah. Hopefully this kind of makes sense to kind of demystify the whole density thing. But that's how it is. So again, here's that table. Your LD max is your best glide speed. So talked about drag. So parasite drag is the one that increases with airspeed squared. So you can just see that going like that in this chart, right? It's that drag curve is the total drag induced and parasite, but the parasite one is the one that keeps you from going faster. It's like that terminal velocity drag. So this is due to the three things that categorize it. So form, it's just the way the aircraft is shaped. Stuff sticking out, antennas, and your landing gear. That's why they put the wheel fairings on, right? Because it's part of that form drag, so that wheel fairing will reduce some of that. The retractable gear obviously will help reduce some of that parasite drag. Interference drag is a little different. It's really where the surfaces meet at angles. So anytime two surfaces meet, there's that nice laminar flow of the air gets disturbed because it's catching on the edge of that. So when you think of something like the B2, the flying wing, there's very few sharp angles in it, right? So it's actually reducing a lot of that interference drag, and as well as making it imperceptible by radar. I think that's part of it too. And then skin friction is really just the fact that air is sticky and it wants to stick to things and it wants to stick to your plane. And no matter what you do on a surface of material, it's going to have roughness no matter how smooth it looks. There's going to be something in it. And then the skin friction is what that air is going to stick to. Yeah, they talked about free stream velocity and the boundary layer. And the free stream velocity is that air that's moving along with the rest of the air around it. And that boundary layer is where the air on your wing is not going anywhere. So if you imagine little air particle guys just clinging onto your rough surface of your wing, just holding there, but then the other guys that are coming by are kind of bouncing off of them. And then as you get further away, you're going to have that laminar airflow over the free stream velocity at that point. The induced drag, this is the one that happens with the air coming out off of the wingtips and racing around, and it creates those vortices. So that's when you're generating a lot of lift and you're very slow. That's when it's going to be most evident. And then as you go faster, those vortices are going to be further and further behind you, and that downwash, that's the relative wind that's redirecting your lift vector, and we'll talk about that. But that's going to be further back and have less of effect on your relative wind. So the other thing about induced drag is we'll talk about ground effect, and there's lots of questions in the written about ground effect, which has everything to do with induced drag. So when we look at the two drags, you'll see this table here, and you can imagine where that parasite drag and that induced drag intersect is the lowest drag amount, and it's probably coincident with the lift to drag ratio on that other table that we looked at, right? So, but as you can see, what this table really tells you is that your induced drag is reduced as airspeed increased, and your parasite drag is increased as your airspeed is increased. So the sweet spot of drag is right there, and it normally is coincidental to that lift drag intersection on the other table. And I need to sip. Sip. I'm thinking so hard right now, I think my face is on fire. Okay, so is there anything back here that you guys need me to clarify, or is this making sense-ish sort of stuff? Yeah? Okay. So the induced drag, right? This is that when you're developing lift and you're going slow, a very heavy airplane needs a lot of lift, right, to get off the runway, to break out of this thing called ground effect that we'll talk about too. So it's generating a lot of pressure underneath the wings that's racing around. And usually it's the point during an approach or the departure that it's generating the most of this. When a large airplane's coming in to approach, it needs to slow down. And it's generating a lot of lift in order to overcome that lack of airspeed. Remember, the lift coefficient has a velocity squared in it. So if you're a big ass plane that's a lot of weight, you're going to have to generate a lot more lift at a lower airspeed. So as a consequence of that, you're down at the bottom of these drag equations. So now your airspeed's down, your induced drag is going to be tremendous, that trying to generate that lift at that low airspeed. So these vortices are flying off of it. So in the written test, I know they ask questions about where you should land if you see vortices or there's wake turbulence reported. And there was a diagram. I don't know if I captured it in here. I don't think it did. But effectively what you want to do is you want to land beyond the touchdown point of the aircraft that's ahead of you generating the wake, because the ground will dismantle that wake turbulence. And then those planes, once they touch down, they slow down really fast. And then you want to take off before the liftoff point of that plane that's generating drag. So you'll stay above its flight path, because those vortices and that downwash goes downward. The other thing they mentioned, I think, is just to stay at an altitude, outside of 1,000 feet of that, because especially below that aircraft. So if you see a jet, if you stay above it, you're generally going to be safe. And if you give it enough time for those vortices to dissipate, you'll be safe from it. So rotating or taking off prior to the preceding aircraft's takeoff, and then approach the runway above its glide path and land beyond its touchdown point will keep you out of that wake turbulence. The other thing that they mention is that a crosswind can actually keep the one side of the vortices over the runway and not allow them to dissipate. Because normally they'll spread off like that. But a crosswind can take, like if it's coming from the left or the right, it will bring those vortices actually into the runway, and they'll kind of hang over it. But it's usually a light crosswind that'll do that. How common is it for big planes and small planes to share runways? Well, a lot of airports have parallel runways, and this is kind of a good point. So that light crosswind can actually bring those vortices over to a parallel runway. They'll use the runways based on the demand that day. So I think my impression has been ATC will give you the big runway if you look like somebody responsible who's going to get off of it. They'll give you the little runway if you look like you're going to dilly-dally and take your time so that you're not occupying the larger runway that the big planes need. Obviously, if you go to an airport that doesn't really have any options, everyone's going to have to get sequenced, but they might ask you to hold or go missed or something, or get out of the way. There's an unfortunate accident that I read about in Houston where somebody, and I believe it was a Cirrus, was trying to land at Houston and had gotten sent around the traffic pattern like 8 times. And on the 8th time, either out of fatigue or just, not paying attention, had, I believe, retracted their flaps too early before they had established a climb. So they had no airspeed, and flaps give you lift, right? So we know if you remove that lift, you change the lift coefficient of the aircraft at a slow airspeed, now you've basically stalled the plane because you've left a safe margin. So they were departing, she pulled the flaps up, and then the plane went into a spin stall, right, as they were leaving that. But she'd been around the lap 8 times, got tired. So that was a little divergence, but it has to do with lift and, lift and airspeed as well. So I mentioned downwash, and again, here's some pictures. This is where we start talking about ground effect, actually. So this picture on the right here shows the induced drag and the downwash flowing behind the aircraft. And when you're close to the ground is actually interfering with that. So another way to think about that is the air that's trying to rush around your wingtips is kind of getting interfered with by the ground and can't come up over the top like it can if it has a nice big open space to do so. So as a consequence of the drag being reduced, you appear to have better lift in ground effect, and the plane will tend to take off earlier than it really needs, earlier than it has sufficient airspeed to break out of ground effect. So to make sure I hit the points on the slide here, the greater the size and the strength of the vortices and consequent downwash, components of the net airflow over the airfoil, the greater the induced drag effect becomes. So you're in ground effect, you don't have that induced drag, but now at the same airspeed, you pull out a ground effect, and that induced drag will hit you, right? Because now it's not being blocked. So you'll see a pitch up attitude happens because it's rearward. It's actually pulling your relative wind down. So if your relative wind is coming at you at the runway, like at your chord line on your angle of attack, right? But then you get up, and that downwish is actually diverging the lift component as a consequence of the relative wind to the back a little bit. And what happens is the plane tends to pitch up a little bit, and you actually don't have enough lift without either increasing thrust at that point to get out of the ground effect. Some people level the plane off, but then they still don't have enough to climb out of ground effect, and then they will run out of runway. So if you overload a plane, you actually don't have enough lift to leave the ground. You have enough lift to leave ground effect, but you don't have enough lift to leave ground effect. You have enough lift to leave the ground in ground effect, but you don't have enough lift to get out of ground effect.
So do you use your rudder to help?
You can't climb out. You just got to land, abort, or dump somebody out of the plane while you're going down the runway.
All right.
But yeah, there's not much you can do at that point. Maybe you get lucky and the air cools just for a second, and then you get enough lift to break out. But yeah, so the main idea here is the fact that lift vector is being pulled rearward because the downwash is redirecting the relative wind, and angle of attack and relative wind in the chord line are all related. So that's really what's important in this diagram. It's kind of this innocuous little diagram sitting in the corner of the book, but that's what it's showing you here. Can you feel ground effect? If you know the plane really well, you can definitely sense it. And once you leave ground effect, that pitching up, you definitely notice that. I don't think about it anymore, but usually what I end up doing is I end up rotating a little bit faster than the rotation speed that they recommend. And once you do pull up, I end up pulling up pretty decent angle of attack on the nose. But then once I leave ground effect, I actually level the nose down to gain airspeed back and then climb out. And I don't know if I was ever taught that, but that's kind of the way I do it. So I know it's coming, so I'm kind of like ready for it. And my strategy is accelerate a little bit faster on the runway, then pull out a ground effect, then use that momentum and level off and then climb out.
Then do you notice it on landing in a similar fashion?
Yeah, in landing what you notice is that you'll tend to float. The plane doesn't want to come down. And certain airplanes with really big wing forms, like they really do that. Also the DA40, the diamond, it's sometimes hard to get it down because it'll just kind of float there in the ground effect. So what you almost want to do is bring the plane in just a little bit lower airspeed.
So do you fly it down from there, or just power back? Or
you just power back and wait, and then eventually you'll settle down. Yeah, it can make it too difficult to grease the landing. That's why actually having a nice headwind on a landing will help it gives you a little more control over the airplane. We'll talk about control effectiveness, because the more airflow you have coming over the aircraft, the more effect you have. So if you have a nice headwind, right, your ground speed is slower because you're going into a headwind, but you have more air flowing over your wings, so that means your controls are more effective. So the slower you go, the less effective your control surfaces are because there's just not as much air hitting them, right? So, you won't do anything. Yeah, so...
It's easy,
Just have to force it to land.
Well, and the funny thing about our Saratoga too is like once it hits like a certain speed, it just wants to drop. So you almost like have to leave a little bit of power in there to encourage it not to do that at the very end. So, but no matter how many times I've landed that plane, it always every once in a while it'll do it to me. And I'm like boom, and then Marcy's like, nice landing. Thank you.
Marcy, you're gonna have fun watching this.
So in ground effect, your thrust is obviously going to be more effective too. So coming out of it, your thrust and your lift are going to be more effective. And then for that same angle of attack. So this is the question that the written will write, and they'll reword it a bunch of ways, and they'll throw double negatives at it. And the FAA questions are really good at doing double negatives. Like you're not in ground effect when you're not. It's like whatever. So just be on the lookout. They're trying to trick you. So they'll ask a question like, the same angle of attack in ground effect is the same angle of attack in ground effect has this effect out of ground effect, is kind of how the question will be. So the answer is that, lift is more effective for the same angle of attack in ground effect versus out of ground effect. But they're going to word the question in a really weirdo way. So yeah, it occurs both during landing and takeoff slow when the induced drag is high, it's greatest. Sometimes people land faster just to have more command on the landing, but then you have a longer rollout too. So if you're in a really strong headwind or strong headwind or crosswind conditions, you'll actually intentionally fly a little bit faster into it to have more control over the airplane. Yeah, so I mentioned that leaving ground effect, you experience a nose-up change in the moment of the aircraft because of that relative wind change and that lift change. And a required change in AOA to achieve the same relative coefficient of lift. So again, that's that description of this effect here. Where you're getting more lift down in ground effect than that, so you're going to have to change something. Usually push the nose a little bit forward, which I think I mentioned. What I typically do is I push the nose down just a little bit after I leave ground effect to restore some of that lift. Ground effect's most noticeable about half the wingspan, so after that you don't feel it as much, and it's really noticeable within a quarter of the wingspan, like 46% of it's down there.
So what's the wingspan like?
The whole, ours is like 40 feet, so half of that 20 feet, yeah. So, yeah, I mean, that's about right. Yeah, so that's right when you're about ready, you're gonna flare out, and you're right there in ground effect, and it's...
So like a big plane that's got 150-foot wingspan.
Yeah, they're gonna experience it much higher.
Way up higher.
Yeah, yep. So, I think I touched on some of these, but the plane may appear to fly before it's actually achieved a recommended takeoff. To fool you into thinking that you're flying. And then as you try to pull out of ground effect, you'll settle back down into it. Because that drag is gonna say, well, you got more thrust there? And you say, I don't have any more thrust. I have no more velocity. So imagine you're running at full power and your plane is giving it its all. And you're just trying to pull out of ground effect. Now, if you have more thrust, you could just add more thrust, right? Velocity, increase the velocity aircraft, increases lift, right? So, and then it actually reduces the induced drag the faster you go. But if you have nothing more on the top end and you're full throttles there, that's why, like I said, there's really not many options you have at that point, yeah. And then we talked about that, the fact that the aircraft may delay a landing in ground effect. Again, what I said, there's tons of ground effect questions in the test pool. I think the Gleim study guide has even, I think, 10 topics on it. So I imagine they can generate 20 questions out of it. They'll just reverse the logic in the questions. But it's something that that's tested pretty well.
Wouldn't coming off the ground a little bit minimize the drag of the wheels on the ground?
Well, you're talking about a soft field takeoff. What you'll do is you'll pull the plane up actually out of the grass or dirt or gravel, right? So there is a technique to help you accelerate in those conditions. So soft field can just be mushy grass or whatever. You have enough speed to accelerate and get up in ground effect, and then you use the rest of that, that drag on the wheels to accelerate and then pull out. So there is a technique, right, for soft fields to do that. There is some technique too for short field but generally that has to do with more with lift, using flaps to take off, giving yourself more lift there, and then you're just going to climb out slower. So as long as you're not trying to clear an obstacle, you can do that too. Add some flaps for taking off. Are high wing planes less susceptible to ground effect? I would say in my experience, no. No. And another thing to think about is that downwash that's coming over the wings and how it's balanced. And and I'm just speculating here, but the the downwash affects the tail and how you balance the aircraft. So a high wing, the tail is going to feel more downwash than a low wing will. And the plane is still balanced out a certain way. I don't think it's going to have any impact, though, on the way ground effect behaves, though. And I haven't observed anything. Although I feel like my low wing floats more, but I think it's just the design of the Piper. And actually, that could have more to do with the fact that the downwash isn't striking my tail as much as a high wing is. Definitely low wings are a little bit different to handle in landing. Okay, so yeah, to make sure I covered everything. Yeah, just make sure, go through the sample questions around this and just feel good about them. The ground effect stuff. Stability, yeah. I'll just be honest with you. This is probably not one of my strongest chapters, but I'm going to push through it with you guys. So the 3-axis, right, we talked about are these imaginary lines going through the center of gravity. And this is the lateral, longitudinal, and vertical. So lateral, easy to kind of think just left and right. And then longitudinal, down through the nose, long through the nose. And then vertical is kind of obvious. So the plane is balanced around these. And when we talk about stability, and I think I talked a little bit about this earlier, so we talk about moments. So if you think of a seesaw, right, and you have a really light kid on one side of the seesaw and a heavier kid on the other side of the seesaw, you would position yourself, right, so that you would either scooch up or scooch back on the seesaw so that you had a nice balance there. So those are kind of like these moments of forces. That in the seesaw case, your body, your weight is a force on either end of this. And if you were to think of you moving in and out as trying to balance that CG of the seesaw. So in the airplane, the CG is that point, that seesaw point in the middle. And the center of lift may or may not be coincidental to that, but it's going to generate a moment. And the further away from that center point, the greater the moment is. So if you've ever tried to balance something, right, you move things either closer to the middle point or further away in order to balance it. You're just balancing the forces. And we'll use the term moment more. It doesn't actually, they mention it in this chapter, but they don't really talk much about it. But this is the term, the calculation term that we use in weight and balance to determine if an aircraft is within its capabilities, its balance capabilities, when we're loading cargo, passengers, and fuel in a plane. So you'll take the distance from that center point, and then you'll basically that distance becomes a multiplier on the weight. And then if it's either after or for of that center line, you'll add or subtract it. And then the number that you come up with is a deviation from that center point, and it will fall in this envelope and tell you if your plane's weighted. Fortunately, nowadays, all of this is done on a flight computer with free software, so you just have to put in the boundaries of that envelope in the software and then enter the numbers in, but more on that later. So as I mentioned before, right, you have that center of gravity and the center of lift, and then way out here is this tail. Well, isn't that convenient? You have something out here that can balance, like think the seesaw again, that can balance that center of lift. And that tail is going to help you do that. It'll put a moment in the opposite direction. And since it's so far back there, it really doesn't take a lot of effort, right? Because it's got that long distance. So if you've ever tried to pry something open, the further back you go on that bar, the more leverage you have. The same idea with the tail, right? The tail's out there. Little deviations in the elevator, and you'd be surprised how little it moves in actual flight, can manage and keep that plane level. So the tail is meant as a means to balance the plane longitudinally, about the lateral axis, and then keep that center of lift and center of gravity in line to maintain level flight. So the other thing they talk, so does that make sense with the moments thing? Does the seesaw analogy actually help? And the pry bar analogy help understand moments and what's going on? So there was some pictures in it talked about this, but there are stability pictures later that show that force on the tail versus center of lift and center of gravity, and that's why those diagrams are there. It's interesting the way the FAA presents the material because they talk about that and then they just go into static and dynamic stability, and I think it would have been better to actually show the airplane getting balanced with the tail at that point. But I'm following it the way they did it, so we'll get back to that tail balancing act. So this is something that appears on the written too. It's this idea of static and dynamic stability. So static stability is just this idea that if you do something, does something go back to where it was? So, or doesn't it? Or does it get worse? That's basically the three categorizations. Either it goes back, it doesn't go back, or it gets worse. So in static stability, and the difference between dynamic is dynamic's oscillation. So if something just keeps oscillating and it doesn't get worse or any better, right, it's actually neutral in that case. So neutral means it does so, but it doesn't try to get better and it doesn't get any worse. So neutral, static or dynamic stability just means it doesn't, you make the change and it doesn't really get any worse or better. So that's that middle drawing here. You push something to another location and it just stays there. It's neutral, it doesn't do anything. Whereas positive, on the other hand, is I've displaced something and it wants to go back to where it was. The spring is a perfect example. You pull a spring and it wants to go back to that spring state. So it has positive stability. If it's a spring on a little hanger, it'll go boing, 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 and that's dynamic positive stability. So it'll actually oscillate to an end. So negative is just gets worse. It's like you push on it a little bit and it's like, whoa, it just, so the image here below is like if you have a truck on the top of a hill and you push the truck a little bit, it's not going to stop. It's going to go down the hill and faster until it hits the little thing on the left side, and then it settles out. But that's the idea and the reason I'm spending so much time on this is there's questions on there written about it. Both of these.
Dumbest diagram in the book so far.
Dumbest diagram is like.
I'm the dumbest. That was for me. I was staring at it and it's like, what? They tell me here.
I know it, and I agree because even when I took the written test, I just memorized these. I just like, okay, whatever. I'll memorize the answers, but then for this class, obviously I have to sit down and actually try to figure out what the hell they're trying to say. So then we look at the dynamic again. Is it getting worse? Is it not? Is it just staying the same, or is it getting better? So you can see the green line is not getting any worse or better. It's neutral. But you see the red line's getting way out of control, so it's diverging, it's getting worse. And then the orange one's not, it's getting better. It's going more back to the center, the stable point. So I try to think of it in terms of that. I thought I actually said those words somewhere. Yes, at the bottom of this slide here. I said positive, it does so, it does restore. Neutral, it doesn't restore, but it doesn't get worse. And negative is it gets worse. And that's kind of the best way I thought of to think about it. So positive, does it get better? Neutral, it doesn't really change. Negative, it gets worse. And then the difference between dynamic and static is dynamic has oscillations, I guess, and static is there's no oscillations. It's just either does, doesn't, or gets worse. Did I cover that enough? Yes. Okay. So there are questions on the written about that, and that's why we talked about it. So back to the tail. Good. I did have this diagram. So you can see the little thing I was talking about, this little system of you've got this center of gravity pulling down, and everything rotates about the center of gravity. But then you have the center of lift that's a little bit behind it, and then you have the tail in the back. And the way to maintain the level, the balance of the airplane is to manipulate that tail. So let's see. Yeah, the wing and tail are the balancing act for the longitudinal stability. So when they design a plane, what they want to happen is that they want that downwash to work in conjunction with the tail. So the airflow is going over the top of the wing, and then it's hitting that hitting the tail surface, which is this lever, this imaginary lever, well, a real lever, right? So when you aggressively nose up the plane, they want that airflow coming over the wing to try to manipulate the tail so it restores the plane, in the opposite direction. And so a well-designed stable plane will just naturally want to do that. So you pull back on the yoke and then you just let go and you haven't stalled the plane, it'll want to nose down. And what it'll do is it'll kind of just oscillate. It'll have this positive dynamic oscillation, and eventually it'll level out without you doing anything. That's the idea. So somebody passes out in the plane for a moment, the plane's not going to crash them. I don't know another way to say that. Well, right. As long as you're not heading towards a mountain. So that's what the autopilot helps with. The autopilot can get you in trouble too, as we talked about last week. So, so now the air flowing over the wing and the propeller slipstream can also push down on the tail. Yeah, depending on airspeed, restoring position. So we'll talk about slipstream in a little bit, but the propeller is creating this big swirl of air that's going around the plane. And you probably guys saw that in the chapter. And it's pushing on different things. It's pushing on the right, the underside of the left wing and the top of the right wing, and then also it's affecting the vertical stabilizer and the horizontal stabilizer. And some of that can actually be used to control the balance of the airplane depending on the speed of the prop or the speed of, the speed of the airplane in that case too. Fortunately, I don't think there's too many questions on that part, so we'll go through it quickly. But here's an example of the downwash with the airspeed and using that lever to maintain that longitudinal stability. That's kind of the summary of what they're trying to talk about here, and they used a lot of pages to say that, but that's the idea. The tail can be used to control stability of the aircraft without you even manipulating the elevator through downwash. And I think that's about all I really want to talk about that one. Right, so I guess it's not. So the center of gravity relative to center of lift also is determining that stability. This is more about weight and balance. So in stability, regardless of what the tail is doing, and the tail can't overcome some of this, I guess is the point. The location of center of gravity relative to the center of lift will determine that stability as well. And I think there's a picture here showing, it's not that one. I don't know if I have additional, yeah, here we go. That's what the thrust line, see, I have to put my words together on this. Right, so the center of gravity is closer to the center of lift. It can be impossible to recover from stall. That's the key point here. So imagine that you can't ever, the center of gravity is so aggressively rearward, there's no way you're going to be able to have enough force or pressure to push the nose forward to get enough airflow over the wing to recover lift. And even if you do, the lift vector is not in front of the center of gravity, or it's in front of the center of gravity. And you're not going to have enough tail force to counteract that difference. It's just the plane's not designed for it. So this is why loading the airplane with an aggressively rearward CG can be super dangerous. Or even if somebody shifts in the plane, like they were sitting in a seat towards the front, right? And then in flight, they move to the back of the aircraft. Now they've effectively moved the CG, and unless you've done a weight and balance calculation for what would happen if I move that person back, you might have actually pushed that center of gravity behind the center of lift and created a situation like this. So the point is that an aggressively rearward aft CG is less stable at all airspeeds. It doesn't matter, because basically your tail's not going to be able to overcome that difference. And it can be impossible to recover stall. The plane's kind of like, if you think about it this way, it's falling backwards, it's getting pulled backwards. It's not, but I mean, that's a way to think about it. So these are questions also on the written. They cover this aggressively or aft rearward center of gravity.
They talk about the planes are designed to be nose heavy so that they'll tip down.
Yeah, and then make the stall recovery easier. Yeah.
Right. So if you fight the design of the airplane.
Yeah. Yeah. It's not. It basically that tail that stability that the tail's designed in, you can't even overcome it. And then no matter how much force you nose forward force you put on the yoke, and that tail is the one that's responsible for making that pitch change. And if it can't overcome it, you're not going to be able to recover.
If you're stalled, you've got boundary separation over the wing, and you're losing lift. I mean, it seems rational you're not going to get lift back if the bottom of the back of the plane after the plane is trying to settle out lower rather than letting you level off.
Right.
If you got boundary separation on the wing, then that's the part that you no longer have the laminar flow over the rear stabilizer.
Well, I mean, the airfoil in the back is a different shape and size, so its coefficient of lift table is also a little bit different, right? So you might have some command on the elevator, even though you've lost lift, and that's fine. But the problem is if you don't have enough arm moment of control on that elevator to overcome that moment of the center of gravity and center of lift, there's no amount of force that the tail can exert in order to recover from the stall, because you either don't have enough airflow over it to give it enough command to recover that condition. So the idea that you can't recover from the stall is you just don't have enough command of that tail anymore. So that previous discussion about the tail being this lever that helps you maintain flight, level flight, if there's not enough design characteristics of the design to overcome that center of gravity and center of lift, and you've fallen outside of the weight and balance window, the tail can't even recover the aircraft. Does that make sense? See, it's an even confusing topic to me, but I think as I talk through it here, I think that makes sense.
Since the front is so much heavier, wouldn't it?
It's about center of, it's about center of lift too, right? So even if your center of gravity is over, if the tail cannot, if the tail is responsible for keeping the plane level, I guess, yeah. So if you can't even, so you can fall out of it and maybe you'll recover or appear to recover, but you don't have enough command of the tail because that CG is so far behind the center of lift or so close to the center of lift, the tail doesn't have enough force on that moment. What's that?
That sounds like a horrible stall.
Yeah.
You got a question?
Has the size of the aircraft affect the need to keep a close eye on CG? Well, a smaller aircraft will. Well, here's the funny thing. It's like a shelf in your house, right? An open shelf in your house will just get things put on it, and eventually there's very little extra space in it. We call this usable load in an aircraft, right? So they make a bigger airplane. Well, that means we can put more avionics and better equipment on it. So, it's like, well, how much useful load do we want this aircraft to have? And that's what it really comes down to. So when you're looking at an airplane, you could take our plane for instance. It's a heavy airplane in and of itself, but its useful load's really small, only because we have an oxygen system, we have retractable gear, we have a turbo in the plane, and that all adds weight. We just pulled out a 20-pound vacuum system, so we get that back. But so our plane has like a useful load of like around 900 pounds, and then that includes the fuel too. So you put less fuel in, you can get more people and luggage in it. But that's the number you're looking at. But so does like a 182 can also have a useful load of the same amount as our plane, but it's a smaller aircraft. So it's really a matter of what other equipment is in the airplane. Another Saratoga like ours that doesn't have all that stuff has a useful load of like 1,100 pounds. It's got 200 pounds more with full tanks. So it's really about, certain planes will be designed for a better useful load, and you have to look at the POH. So this is not really a direct correlation. there was a Piper Aztec. They used to call it the Az truck because I think it could carry something like 1,500 pounds of useful load, and it was just a 4-seater plane or something. So, yeah, it really just depends on that. The Cessna Caravan is a huge cargo plane too. There's like a 12-seater high-wing Cessna. It looks really ducky. It has like luggage bays on the bottom. Have you ever seen one? But they use them in the bush a lot. High-wing, you know.
It's up for sale in San Francisco.
So you are looking.
That's what you're looking for. An air
It is. It's break time. It's break time. Oh my God! It's break time already. Okay.
15 more minutes or no? Or-
No, it's 7:15.
Okay.
Yeah, it's break time. We'll take a break.
So, are we on break now?
We're gonna break right now.
So should we be doing the app test already, considering we're only into
Well,
chapter 5?
No, if you have the Glime book, I have set out the study unit. The study units.
Talking about the book that was right here?
Yeah, this guy. Yeah, this one right here. So.
I just got it the other day.
So like, you're ready to look at study unit 1 after today's lesson if we get through all the topics.
Okay.
So then I'll say, I want you guys to go ahead and give it a shot. I also have progress checks on the syllabus. So what I'm probably going to do is do probably some written form questions and some multiple choice. The written test's all multiple choice, but, and I'm not sure how I'm going to do it because I can't moderate the people that aren't, here in class. I just have to trust them.
This is for us, right? It's for our self-checking to see how.
Yeah, I mean, you're only cheating yourself if you cheat,
Right,
so.
right. Exactly.
We're looking at you, Brad.
But yeah, so at the end of when we cover enough material, I'll say, okay, go run through the Glime study unit 1. And study unit 1 at the end of this class, I'll ask you to look at. And then after next week's class, probably midweek, I'm going
I
to.
was wondering how we were going to monitor our progress.
I have 2 progress checks. So after next week's class, I'll write up some kind of a quiz or something, a take-home thing or whatever during the middle of the week.
Okay.
And then we'll just bring it back and maybe spend a half an hour going over it, So, yeah. It's break time, but if there's any questions to you out in the ether, go ahead and bring them in. I'm going to go ahead and put the standby screen on right now. And we'll be back. We were talking, we're talking about stability and center of gravity and the tail's inability to overcome a rearward CG. That will be on the written for sure. This one not so much, but it's interesting. If the CG is higher or lower than the thrust line, you'll notice it because as you increase thrust, increase the propeller, the plane will either pitch up or pitch down. So thrust can affect that stability. I have seen questions in the written about this, but maybe not in the private written.
Is the thrust line pretty much analogous to the longitudinal axis?
It's usually, yeah, you want it designed with it, but obviously if you load the vertically in a weird way, you might have a thrust line that's not, aligned with the center of gravity anymore.
Where you're carrying gold bars. Or
Yeah, they're way on the floor, yeah. Or if you put stuff way down in the, I didn't even think about that, but sometimes I put stuff on the floor in the back of the plane, like my luggage and stuff. So it may be below the center of gravity line. So I'll have to pay attention and see
on
if.
the seats next time.
Yeah, well, I still, and it's just me in the plane usually when I do that, so. The plane flies wholly different when it's just you. A heavy plane like that and you're by yourself, it's the weirdest thing. Or with Ryan, my friend Ryan, he's like kind of a smaller guy, so like the same. Just kidding, Ryan, I love you. So there's some things that in the design of the plane that they can do to help with lateral and directional stability, and I've seen these questions in the written. But lateral or dihedral, lateral stability, they'll have a dihedral, and what this is and you see it on planes, but basically the wings are bowed up from the bottom out, and it's the longest time I really get what was going on. But so the wingtip's higher than the root, And what happens is if you catch wind on either side, the angle of attack on the far side wing is going to be different than the near side one, right? If it's flat like that, they're both kind of hitting the wind at the same angle of attack. But when they put the dihedral, it actually causes the one wing to want to lift up and level off, and that can give you additional stability. There's another thing on for directional stability with a swept back wing, and this one is kind of interesting, but if you think about it a little bit differently than the book presents it, imagine you're looking at a plane from the front and the wings are swept back, right? Or if the wings are not swept back, right? It looks the same from the front, right? It just looks like there's wing. But if I turn the plane like this, that looks different. Almost the one wing on the right kind of disappears, right? If it was flat, the wing on the right still sticks out a little bit, right? So the front wing, now that it's swept back, it kind of disappears. So there's more drag, right? And that wants to pull the plane forward. I don't know why they don't explain it that way in the book, but that way makes sense to me. So the drag differential between the forward, when they say forward wing, they mean the one that's facing into the wind, and the aft wing, which is the one that you kind of can't see in that front profile. That's what pulls the plane back in directionally stable. Other things, obvious things like the vertical stabilizer, the fin in the back is going to try to pull the plane directionally. It's weather vaning. Weather vane only wants to line up with the wind and have the least amount of resistance to the wind. Also, the surface area of the side of the fuselage will help with directional stability. But even with the stability, you're still going to have to provide some rudder influence to keep it from oscillating or to get a quicker, stable result. When then we talk about the oscillation, there's this term that comes up called Dutch roll. They mentioned in the book, and I think the only reason this shows up on the written test is because Bonanza V-tails are subject to it. So, but the Dutch roll is a coupled lateral and directional oscillation that is dynamically stable. In other words, it's neutral, right? It doesn't get worse, it doesn't get better. But it's just because of its oscillatory nation, you have to be on top of it and to get rid of it. I've seen the Dutch roll question show up in the test. So, but it might not be in this year. It shows up every once in a while. Cool, we finished that chapter, that section. Now we're, part of that chapter. This is another section in that chapter. It should have been 2 chapters in my opinion. So, right? I know. I mean, that would have been a good breaking point. But yes, alas, we are not out of the chapter 5 material yet at this point. So, forces in turn. So this is, this topic's important because of the loading, and mainly because of the loading, and also to get your mind around how a plane actually turns. And unlike a car, the wheels are grabbing the road, and then that's what turns the car, right? But you can feel centrifugal force in a car, too, in that case. In an airplane, what we're doing is we're actually banking the plane with the use of the ailerons. And then we have to introduce a lift component horizontally to pull the plane into the turn. So you bank the plane and you'll pull back a little bit on the yoke to add more lift. And that lift not only pulls it into the turn, but it has to counteract the centrifugal force. So as a consequence of that, you're actually increasing the relative weight of the plane, or what they call load of the plane, right? So now you've made a plane that weighs 1 g weigh something that's not 1 g. And this has all sorts of effects on how how much excess lift, how much extra lift you have available in that turn. And also, you're going to need to increase the angle of attack, right, in order to get more lift, right? so your margin between your critical angle of attack is narrower. So, like I said, it's banking and lift that makes the turn. So yawing and using the rudder pedals it'll point the plane's nose, but it will not actually begin a turn. You can do some tricky things using the stability of the aircraft as an aid. You can push on a rudder pedal and it will kind of like fall into a bank and then start turning, but it's not really it's not really what's the kind of turn that's going to keep you level. So it's lift that's turning the plane because of that horizontal component, and then the banking through the ailerons is redirecting that lift component so that can pull you into the turn. So obviously we're stealing lift to turn the plane. The plane will descend unless we increase the overall lift to compensate for this. So we're stealing that lift vector, now is pointing inside, so if we maintain the same amount of lift, we're going to start descending, right? Because now the vertical component of lift is smaller than weight, we'll start descending. So we either need to increase the angle of attack or increase the airspeed velocity to increase lift to overcome the loss of the vertical lift component. Okay, so so centrifugal force and weight combine to create that resultant load. So you also need additional lift just to overcome that load, not alone the fact that you've redirected that lift vector away from weight. So so a lot of things going on in a turn. So as I mentioned, additional amount of elevator force to increase the angle of attack or an increase in airspeed. So you can turn the plane and then you can just increase the airspeed and you won't lose altitude, because remember the lift function, right? Airspeed will increase lift. Or you have to go to a different angle of attack. So pulling back on the elevator will change the angle of attack, giving you more lift up to a certain point, right? Right. So we still need rudder pressure though, because when you bank the plane, when you first bank the plane, what's going to happen is you're going to put the aileron down right on one of the wings. So we've got a little fake plane here, but you're going to change the camber of the wing, right? So you're actually going to induce more drag on that wing. This is the wing that's going to lift, right? So you're changing this wing, and then you're also changing the inside wing. You're changing it up like the other way. My plane's falling apart. I didn't know how well that would work, but so the drag on the wings is different, and also the rate at which each wing is going through the air is different. So the type of lift forces on each of the wings is a little bit different, and it causes the plane to kind of point in the opposite direction, and to compensate for that, you need to kick the rudder in. So the plane will naturally want to slip in a turn. In other words, point outside of the turn. So you'll bank the plane and it won't want to actually come around. It'll just kind of want to slip into the turn. It'll want to just do that. So you kick the rudder pedal to coordinate it. And then when you coordinate it, now you're getting even airflow over both wings too. And that's important. And once you've entered the bank, your wings will actually level out because you don't need to bank anymore. You're already banked, and now you've established your new component of lift, and you're in the turn. But you're coordinating it with the rudder. If you put too much rudder pressure in, the plane will skid. So the nose will point to the inside of the turn, and then you'll be kind of like skidding around the turn. I hope you can't really see it on the screen, but so the nose is pointing deeper into the turn than what you need. So what you really want is you want that perfect balance. There's an instrument in the airplane called a turn coordinator, and it's just a little bubble that sits in like a thing that looks like a level, and then that will tell you if you're skidding or if you're slipping through a turn. It's basically sensing center of the centrifugal force of the aircraft, and whether or not the net load is pointing directly down. If it's pointing a little bit either way, that little ball will swing, and when you're taxiing, the little turn coordinator ball will swing around as you're turning the plane because of the forces, the centrifugal forces turning the plane around. So So as we mentioned, right, you're going to be closer to the critical angle of attack in slower flight, right? Pulling back on the elevator, not going faster. And if you don't have if you don't coordinate the turn, one wing is going to tend to stall before the other because you're not having even airflow over it. So unintentional, uncoordinated flight near the critical angle of attack is dangerous. So this is John Denver, by the way, while executing a turnout climb or slow turning descent. So he might have, I think he was either in a descent or a climb out, pushed on the rudder, probably was in a turn, slow flight, close to the critical angle of attack, trying to reach for that fuel selector. So it's super dangerous if you have uncoordinated flight in slow conditions. So, so in these cases, yeah, it's you're low to the ground, you have insufficient time to recover the stall, right? You've slow, uncoordinated, stall, one wing stalls greater than the other, it kind of falls. You see these two, a lot of accidents happen around this, numerous ones, usually anything in the pattern where the plane just appears to fall out of the sky for no reason at all. That's it. That's the one right there. Unless it's fuel starvation or something like that, but that's typically the one that'll do it. So in a constant rate level turn, as the airspeed is increased, the radius will increase. So like we said, you can either pull back on the elevator in a turn to get more lift, or you can increase the airspeed. Well, if you choose to increase the airspeed, the radius of the turn is going to go longer. But increasing the angle of bank will increase the load, which will reduce your safety margin from stalling, right? So there's trade-offs there. What we see a lot too is that hastening a turn from base to final. Base to final is the last turn you make when you're going in an approach and pattern work. Somebody will steepen the bank of the turn and increase the load, and they're already going slow because they're approaching, and then the plane will enter a stall. They're so close to the ground they can't recover. So here's a case where, again, uncoordinated flight is going to be a huge culprit here, and you have to really, if you're going to make that tight turn to base to final, you better well be on your stick and rudder skills and have that airplane coordinated, or just go around.
Do that 8, huh?
What's that?
You have to do that 8.
Well, there's all sorts of flight maneuvers that help with coordination. But yeah, basic pattern work is if you're doing that base to final, and I experienced pilots do this in crash planes. They don't want to miss final, and they'll turn it hard, and they'll pull it back. They'll increase the load. They'll reduce the safety margin. They won't be coordinated. One wing will fall, and they'll crash to the ground. So I don't know how many of these I see. I would say probably 60% of the accidents I see, I can tell right away just by reading the description of it that this is what happened. So it's you got to be on your game when you're doing those turns going slow. Again, just this diagram. The turn is actually caused by Harrison Ford ended up on the ground on the golf course. Oh, you think he stalled it in a turn and didn't quite. Well, he recovered on a golf course, I guess.
Which Harrison Ford incident this was?
Yeah, which one was it? So again, the plane is turned by the horizontal component of the lift. Rudder, the application of rudder ensures even airflow over both wings. You don't want one wing.
If you go too slow, that it could stall out then too. If you're going too slow.
If you're going, you cannot. Yeah, you can't make the turn. If you're going too slow, you're not going to have enough lift to make the turn, and you could stall the plane in a turn as well. Yep. Yeah. So this is the other kind of fun, wacky one to think about. To initiate a climb, so we know in a turn, to make a turn happen, you have to move lift into the inside of the turn. But to initiate a climb, you actually need to increase lift momentarily, though, not forever, because lift is a force, and a force accelerates. And then once you've got a velocity established, you don't need additional force. But when you initiate a climb, you have to overcome weight. And now your lift vector, right, is going to be perpendicular to the relative wind. So it's not pointing straight up anymore. It's kind of pointing back. So when you establish the climb, you still have to have vertical component of the lift equal to weight, just like in level flight. But part of your component of lift is pointing rearward. But all that really does is slow your ground speed down. Your airspeed is still going to be the same. But if you slow your airspeed, you have to increase your angle of attack to have the same amount of lift. So typically, once established in a climb, you'll need additional power to maintain the climb and not slow down or speed up. So that's why we say that in the established climb, the angle of attack will approximately be the same as that at level flight. It's just that you have a little more thrust, right, to make up for the fact that your one of your components of lift is not helping you out anymore with the weight or the Yes, the effective drag. I'm sorry, I did like getting this confused. It's the effective drag at that point. It's some kind of point. There's a diagram that helps with this. Man, I don't know. Maybe I'm only good for like an hour and a half. Yeah, so when the flight path is inclined upward, a component of the aircraft's weight acts in the same direction as and parallel to the total drag of the aircraft, thereby increasing the total effective drag, which is overcome by additional thrust. So the thrust is needed to overcome the component of weight that's acting in the direction rearward, because the plane's faced like this. So relative to you in the plane, the weight's pointing kind of at an angle towards drag. So the lift, and this is what I was saying, the lift component still, it points slightly rearward, but only relative to ground. And this kind of goes back to Brian's question originally, which was like in a climb, like the angle of attack is going to be relatively the same as level flight because your relative air is flying over the wing in that same way. It's just that your ground speed will slow because the lift component is actually slowing you down, so to speak, right? It's pointing kind of rearward relative to the ground, but it doesn't slow the airspeed. So here's this picture showing that to initiate a climb, you increase lift, which will start accelerating the aircraft upward, but once you've gotten to your climb speed, your climb rate, the lift is relatively the same as level. And then again showing this direction of weight. So if you're relative in the airplane here, I can draw this little thing here, but you can see that weight components also relative to the aircraft's point is also pointing in the direction of drag, so the net drag is going to be greater, and more thrust is going to be required in order to maintain that climb. The big point here, and I think in the written, is that to initiate a climb, lift must overcome weight. But eventually, everything equalizes. Your angle of attack is still going to be the same. You need more thrust to overcome the additional components of weight on drag. Okay, do those two make sense? They're just kind of a different way of thinking about it, right? So this is why it's important to think of force. Isn't velocity. Force is accelerating. And if forces are balanced, it either remains not moving or it remains at whatever velocity it's at. So to initiate that climb, you have to increase lift to accelerate it, but then once you establish it, you just need to balance it out. So the first paragraph on stalls in the handbook are great. These sentences are all from the first paragraph, and they're probably the best sentences in that entire chapter. So an aircraft stall results from a rapid decrease in lift caused by the separation of airflow from the wing surface brought on by exceeding the critical angle of attack. We've talked about this the whole hour and a half here, right? So that's what causes the stall. But the wing continues to produce lift. You saw the chart, right? Even at that critical angle of attack, there's still a little bit of lift on the other side of it, right? If it didn't, the plane would actually just fall out of the sky like a rock. A stall can occur at any pitch attitude or airspeed, right? Because it's all about relative wind, chord line, angle of attack. It has nothing to do with weight and airspeed, right? Stalls are one of the most misunderstood areas of aerodynamics because pilots often believe an airfoil stops producing lift when it stalls, and that goes back to the point I have on the left here. A wing continues to produce lift. If it didn't, the plane would fall out of the sky. In a stall, the wing does not totally stop producing lift. Rather, it cannot generate adequate lift to sustain level flight. Each aircraft has a particular angle of attack where the airflow separates from the upper surface of the wing and the stall occurs. The critical angle of attack varies from approximately 16 degrees to 20, like that chart, right? Depending on the design, right? But each aircraft only has one specific angle of attack where the stall occurs on the wing, right? There's that chart again. Damn. So here's that coefficient of lift and that critical, critical angle of attack where the wing stalls. Again, it's the angle, the angle between the chord line and the relative wind. So what kind of stalls? We can categorize a low speed stall. We talked on this a little bit, right? You know, you're flying really slow. Lift is, velocity squared. So a low airspeed, you're going slow, you're gonna have to have a higher angle of attack in order to make up for the fact that you're going slow because you have more lift at that slower airspeed. So the airspeed slows, the angle of attack is increased to produce that lift and maintain level flight. You're also increasing induced drag, so you require additional thrust. And then you feel this buffeting. So in flight training, what they'll do is they'll call this slow flight. It's really crazy. So imagine this, you pull the plane into slow flight. You pull the power back to slow the plane down. Then you start pulling back to maintain altitude. So the instructor will say, okay, I want you to enter slow flight. I want you to maintain 3,000 feet. So you pull the power back to slow down. And he says, I want you to maintain 3,000 feet, and I don't want you to go any faster than 60 knots. So you slow the plane down, you pull back. You're pulling back, you're pulling back, you're pulling back. All of a sudden, your altitude starts dropping off. And we're like, holy crap, you got to put the throttle in. Pretty soon, you practically have the throttle all the way in, and you're flying at like 60 knots just to keep the plane flying. And the stall horn will go, it'll be barking at you like you're right at the end of it. But the throttle is full. It's the craziest thing. But that's why you have to overcome that induced drag to maintain level flight. Slow with that high angle of attack. The plane is like this and you're going 60 knots and you got full throttle. So it's a really good way of demonstrating, and this is potentially a phase of flight coming in for a landing, right? So when you're just about to flare out, you're going to be close to this configuration. If you're doing a short field landing, you'll be in this configuration, and if you're really experienced, you'll be toying with this configuration as you're trying to limit your landing distance. So all these short takeoff and landing guys are experts at riding the fine line between stalling and slow flight. So as a matter of point, I tried to do this in the Saratoga and it doesn't like it, as I noted in the blistering of my engine cowling because I didn't have enough airflow through the engine compartment to keep it cooled when I was doing this. So we don't do that anymore.
Expensive.
Yeah. I mean, I'm more worried about like the turbo burning out or something. And so, yeah, I think I flew slow flight for like 5 minutes, and don't do that in a Saratoga. But these training planes are, yeah, do it in a rental. This is the interesting one, this high-speed stall, right? So again, this is relative wind and flight path, angle of attack. So I added these little arrows on the drawing from the book, because they didn't have this, but think about when you're pulling out of that dive, right? At that point, the momentum of the aircraft is still going down like that. So if the relative wind, and you look at that angle, it's pretty clear that you're exceeding the angle of attack at that point. And that's why you're going to stall the plane, trying to recover from a stall. It's kind of funny. So, expert aerobatic guys know exactly how much force they can do on the bottom of one of these fancy maneuvers to not stall the plane again and to manage that. So in a steep dive to a climb, the relative wind versus the chord line is near the critical angle of attack. We see that there. The momentum of the descent has to be overcome. So there's an additional load factor. And the second stall can occur while trying to recover from the initial stall. So not only do we have relative wind working against us in angle of attack, we also have an additional load on the aircraft that the lift is going to have to overcome. So there's a bunch of things going on there. Turning stall, we talked about that too. Again, the load factor is increased, so the lift has to increase to maintain level flight. You get closer to the critical angle of attack. Talked about all this. Uncoordinated flight can cause one wing to stall more. Both wings stall, but one stalls more than the other, and then you can result in a spin, which is really hard to overcome. You'll see this table here in the tests in different forms. It might have the load factor curve only. But it'll say if the load is 2 Gs, how much more of an increase is there in stall speed, or what's the new stall speed with a 2 G load? That'll be in the test. More on propellers. It's a rotating airfoil. I keep saying all these airfoils everywhere, but the propeller's another one. So all the aspects of aerodynamics we discussed before apply, that lift and that drag formula. Obviously, the engine's the high pressure side of the airfoil, and it's higher than the atmosphere. That's what's drawing the plane forward. The fact that a propeller or an engine power can never exceed 80% has always been interesting to me. In our airplane, we have an engine gauge that tells us the percent power that the engine's delivering, and it will never go above 78%. And I'm like, well, that's not fair. And it turns out it's because the slip of the propeller and the friction on the propeller is what prevents the engine from being able to deliver, 100% on the propeller. And it's not that it's possible anything can deliver 100% power delivery, but in this case, it's because of those two factors of the propeller. So what they talk about as slip is if I put the propeller in some imaginary liquid that was perfect and I turn the propeller, how far would the propeller move in that, And that's like, ideally, I'd want it to move that far. But the reality is it doesn't move that far. And that's called slip, propeller slip. Right. The other thing is just friction. Again, it's just the bits of air sticking to the propeller that prevents some of that. Yeah. So the difference between the fixed pitch propeller and the variable pitch or the constant speed prop. The fixed pitch propellers will operate that 80% efficiency, that top efficiency, but only in certain configurations, and usually it's cruise. But a variable pitch propeller, you can adjust the propeller and the engine power delivery in order to balance it out and get the most efficient operation depending on what phase of flight you're in. So we talked about twist last time, and again, it's just to make sure that the propeller has constant angle of attack along its blade length. So again, it's the relative wind, and the forward velocity is going to be different on the blades. So the blade's actually designed, if you look at the cross section, designed differently so that its lift is approximately the same. Zach had a question. The planes that we learn on, they may all be fixed pitch, but I've seen training planes now have a prop control on them. So it's not uncommon to see it in training planes now. The Diamond, the DA40 or the DA20 has a prop control, I'm pretty sure. So,
And bad fuel lines.
what's that?
And bad fuel.
And bad hoses that rubber, dissolves in gasoline. So the twist in the propeller blade, if you look at the cross section, you can see that the airfoil shape is a little bit different. So what they do is they realize that the velocity, the inside of the hub is traveling slower than the outside. So they design the propeller blade so that the angle of attack delivers the relatively same amount of thrust across the propeller, depending on the airspeed of the velocity speed at that point in the propeller. So that's where you see these diagrams in here. The inside near the hub is traveling slower than the outside, so they change the pitch of the blade and the design of the blade at that point so that it delivers approximately the same amount of thrust throughout the rotation. Again, it's all about angle, attack, chord line, relative wind, and velocity. Velocity being part of the lift equation, again, also applying to propellers here. So the prop has this, some effects. They call them left turning tendencies. There's a few things, like one of them is just the fact that when the propeller turns, the plane wants to go in the other direction, right? So how does the number of blades impact performance? Yeah, that's a good question. I mean, what the relationship I've seen is that the number of blades usually has to do with the amount of torque that the engine can deliver. So smaller engines you'll see typically have 2 blades. I mean, you never see, somebody did make a mono blade plane, actually. You know, you can probably look it up online. It just has a counterweight and it has it has one blade, but it has a counterweight on the other end.
Yeah.
It kind of looks like it got hurt or something.
Just for theory?
I don't.
Just to prove you could? I'm afraid of it.
I don't know, but yeah, somebody did a mono. Yeah. But yeah, the relationship I see is it has to do with the amount of torque that the engine can deliver, and also, obviously you're looking at the friction on the blade, and more blades is more friction, so the engine's gonna have to overcome that. Well, it can be more efficient depending on the engine, right? So I see turbos have 5 blades. Some turbos, turbine engines have 5 blades. I'm not sure if I've ever seen a reciprocating engine have more than 3. Maybe a turbocharged one, but it kind of has to do with how much torque the engine can deliver ultimately. Yeah, I would have to look more into that because it's a good question, Ryan. I think I'd like to know more about that. I might look into that. So the torque reaction is the blade, the propeller twists one way and wants to twist the plane the other way. It's just what happens if you hold a fan and turn it on, you feel the fan kind of go the other way. So it just causes rolling to the left. So that'll cause a left turn. And on the ground, it can actually just cause the tire to push more on the ground, and it'll actually kind of pull the plane off. I feel this in our aircraft when I push the throttle forward. I can really feel the plane wanting to pull me a little bit to the left, so I have to counteract that on the roll out. The slipstream is this air that's corkscrewing around the aircraft. This one you typically feel more in like something that has a really big vertical fin in the back, because a lot of air is hitting that and wanting to push that tail off to the right, which makes you turn to the left. So that will also strike the underside of the wing and on the top side of the wing, so causing a rolling to the right. Gyroscopic action. I actually have a demonstration for this one. This is yeah, and the reason I have a demonstration for it is because it's like really kind of a weird thing. But the idea is that your propeller is a big gyroscope and it's spinning, and then when you rotate the plane or change the direction of the nose, it's actually pushing on that gyroscope, and the gyroscopic action creates a force that's 90 degrees ahead of and in the direction of the rotation. So the best way to demonstrate it is actually just to use a gyroscope. So I'm going to spin this little guy up. Yeah, it's really prominent with tailwheel more than anything because they're changing the pitch of the plane is the greatest. And a tricycle gear is kind of level like that. You'll notice it when you pull up, but let's see if I can do this right. So here's our gyroscope, right? So when I gotta turn it the other way. So imagine you're going down the runway and you pull up. You see how the gyroscope pulls to the left on me like that? That's the gyroscopic action. So you're just rolling along and then you rotate the plane, it wants to pull you to the left. Anyone want to play with this?
So left turns are easier.
Well, you're going to find you're pushing on the right rudder pedal a lot more often, so that's for sure. I love gyroscopes, they're really cool. This one even came with a string and you can hang it. If you really want to learn why gyroscopes do what they do like that, there's some really great videos where guys take bicycle tires and hang them from strings and talk about momentums of the velocity and explain why things like that happen. So there's a little stand if you want to make it stand too. What happened to the string? So that's the gyroscopic action. I hope that conveyed over the video as well. Another one that's a little more complicated to understand is this asymmetric loading, and the idea here is that the propeller blade mainly in a climb is cutting deeper on the downstroke than it is on the upstroke because the angle of the attack of the blade and the relative wind is different. So the center of thrust then, because that downside is taking a bigger bite, is the right of the center line, and then if we remember everything rotates about the CG, your center, if your thrust is over here, it's going to rotate you that way, it's going to pull you that way. So if there's a little string on the right side of the plane pulling, it would pull the plane that way. So it's going to give you a left turn.
The plane just always wants to point to the left.
Yeah, and unless the propeller rotates in the other direction, then they all become right turning tendencies. So what did I say? I think all these things are if considering clockwise rotation viewed from the pilot's perspective. Yeah, that's why I had the gyroscope backwards. Remember, I did it the first time and it went the wrong way because I had it.
It's an English plane. We talk about
Well, yeah, it's.
other things.
They said in America, for the most part, it's clockwise. Yeah. Things get funky with multi-engines. I know we're not talking about it, but it's important to know the center of thrusting comes up. If you have if you have a multi-engine plane and one of the engines dies, right? They have this thing called the critical engine, because what happens is that center of thrust now isn't balanced anymore, and now you got this huge center of thrust that's way out there. And usually what they say is during a takeoff, if you lose an engine in a multi-engine plane, just make a landing, because you're too low to the ground to climb. You'll be able to maintain flight, but you're not going to be able to climb. You don't have enough thrust. If you imagine, right, you're slow on a climb out and you lose thrust. So you're going to have to increase the angle of attack, but you're probably already close to the critical angle of attack. You don't have additional thrust, so you're kind of screwed. Yeah, so this diagram here from the book shows what I just showed you with the gyroscope, right? You pull it up and then it goes off to the left. And then this asymmetric loading is just showing that here's an airplane in climb. I don't know why the yellow down arrow is like that, but to my understanding, it's pulling the plane in to the right because that downward biting blade is going to be pulling deeper. There'll be a question about. There won't be a question about asymmetrical loading, but it'll have like a list of things and then say, which of the following are left turning tendencies? And then they'll say gyroscopic precession, and then they'll throw in a weird word like monkey butt, and then, asymmetric loading, and you obviously don't pick the one that has monkey butt in it, so, no monkey butt. Weight and balance, again, we'll talk more about that, but we did talk about load factors, right? Load factor is g-forces. Most obvious in a steep turn, but also trying to pull a plane out of a deep dive can induce g-forces. You can also induce negative g-forces, and planes can't always handle all those either. So if you go into a climb and then you nose over really quick, you'll have a negative load upward. Fuel in a gravity-fed plane might not actually get fed into your engine because it's no longer gravity working with you anymore. So, so mainly though, it's a centrifugal force thing. Either, like I said, from pulling, well, no matter what, it's centrifugal force. Whether you're pulling on a dive, you're in a turn, you level off sharp in a climb. So I talked earlier about excess load, or excess lift. So excess load is the amount of extra load above 1G that a plane can actually, carry. And that varies directly with the speed and excess lift available. So if you have excess lift, you can carry excess load. If you have more G's and you have excess lift, you can handle them. And this is the term that the written test actually uses. So very little excess lift is available. It's low at a low airspeed, right? Because you got this huge angle of attack, right, to make up for the fact that you're not going fast. So you can, if you overload a plane, you don't have any excess lift, you can't overcome that load factor, and you won't take off. The movie American Made is a perfect example. This guy's trying to load the whole plane up in the high altitude, low density airport. At high speeds, lift is great. It's already awesome. And the loads, you could think, wow, man, I can carry lots of stuff here. I got so much lift. But now you're coming up on structural capabilities of the aircraft. And in this case, the load is raising the stall speed so much that an abrupt motion can actually damage or cause the plane to stall. So high speeds, they actually have a speed that they designate for turbulent air that prevents the loads from exceeding the structural capability of the aircraft. So they'll tell you to fly maneuvering speed in turbulence so that an excess load won't destroy your aircraft. Right, so that's what this is saying. The plane will stall at a higher speed. The plane will stall at a higher airspeed. That does not mean better, that means worse, right? So instead of stalling at 50 knots, it will stall at 100 knots with that load versus a normal load. So there's less margin of safety from stalling. If you're going 100 knots or 110 knots and now your load means your stall speed is at 100 knots, you only have 10 knots of margin, where if you don't have that load, you have 60 knots of margin. That's another way to think about it. So, and this is like if the load factor is 4 Gs, which is crazy amount of, I don't know when people black out, but it's got to be close to that. So what can bring about loads? Like we said, turns, obviously centrifugal force in a turn. Then they were pretty significant over 45 degrees. So stall speed is increased rapidly with that load, and the significant angle of attack is required to generate the required lift, and there's less excess lift available. So that's pretty much what I mentioned earlier, but stated in this section. Stall recovery can introduce a load that re-enters the stall because of the flight path momentum. We talked about that. And then additionally, the recovery G-forces can actually exceed the load limits of the aircraft, tearing the wings off, imagine, right? Or worse, well, I don't know worse, hidden latent damage. So structural damage you can't even see inside the plane. And thinking, oh, the plane's fine. But it really isn't. A spin recovery can also induce some severe loads. And as I mentioned, rough air, high airspeed means the high lift, right, on the previous slide. So that means high load, and if you hit a bump or something, you could actually exceed the load limit of the aircraft. So there's this maneuvering speed that they recommend. If you enter turbulent air, reduce your airspeed to avoid that. This is that diagram that was on the other page, but this only has the load factor curve on it. And you'll see this in written tests. They'll show this chart and ask you to tell them how much, this one, how much of a load there is in an angle, or it'll probably have the one with the stall speed, which says, if you're in this bank angle, what's your new stall speed? Another one that they'll covers is VG diagram. So it's a velocity versus G factor loads. And the table's really only valid at a certain weight and altitude, but they want you to understand how to read it. We'll probably do this more later on. I think there is in the study unit 2 in the Gleim book some questions around this table. So most normal category planes, like what we'll do for flight training, they're good for about 3G down to -1.5. A utility category has a little better load capability, so 4.4 to 1. 7 negative, but the aerobatic is the extreme side of things, can handle a lot of G-forces. Utility category can be used for doing some spins and stall recovery. The aerobatic definitely. Aerobatic can be used for a lot of fun stuff. A lot of fun stuff. Again, maneuvering speed. Safe, full movement of any one control. And it varies for flight conditions. So they don't actually put it on the airspeed indicator. It depends on different conditions of the aircraft and how it's weighted. Then there's maximum structural speed. So this is the yellow arc area. So between the VNO and the VNE is this yellow area. So this rough air, that'll do the latent damage, something worse, something bad, if you hit rough air. So you can go in there, but you should only do it in smooth air, and don't ever manipulate the controls aggressively. Never exceed is basically parasite drag will tear your plane apart. It's never intended to go that fast. So that's the red line. If you do it in the flight simulator, it will end your flight simulator session. That's how I have it set up. Here's the VG diagram table. I mean, it's just something you look at and learn where the different points are. But these, it's like the green arc and the yellow arc and then the red line, basically. And then there's G-forces on the top and bottom that indicate if you exceed these, regardless of, you know, that airspeed window there, you're going to cause structural damage. So it's basically the load capability. The orange area would be the interior damage or things that you maybe don't see getting damaged in the plane. Weight and balance is something we'll do actual equations for, but in highlights, there's this idea of a ramp weight. The book doesn't talk about it, but I'm talking about it. You'll see ramp weight in weight and balance tables. Basically, this is how much can the plane actually carry on the ground. And we always talk about weight and balance in flight and instability in flight, but man, if you overload a plane on the ground, you could have a prop strike going over some crappy asphalt. You could damage the strut. You know, you could wear the tire weird. Wait, Ryan asked, doesn't altitude impact never exceed 2? Wait, yeah, reword that question and I will get back to you on that. I'm not sure I understand. Yeah. So the practical ramp weight is, you know, just protecting your airplane driving around on the ground. The other thing is, like, available space in the plane and fuel tanks doesn't mean it can be filled. That's the other thing to remember. Just because there's available space doesn't mean the plane can actually carry it. Unless you're filling it with, say, peanuts, like popcorn peanuts maybe? Yeah. Some feathers, yeah. But 100 pounds of feathers still weighs 100 pounds. Go figure. Again, the movie America Made, there's a great scene in it. You have to check it out. Yes, and aerobatic planes must be loaded sensibly, because what we learned is if the center of lift and center of gravity aren't balanced correctly, then a recovery from a stall can be impossible. So, does altitude impact never? I mean, I didn't get the feeling that it did. But maybe it does. This says yes, yeah, certain weight and altitude. Yeah, that's what. There's a bullet point there. Yeah, is it altitude or attitude? Altitude, and I didn't read about that. Why would altitude impact this? The density of the air, perhaps. I would guess. Nope, I'll have to go look that up. It's so good having you in the class, Ryan. Yeah, so aerobatic planes have to be loaded sensibly because of the center of lift, center of gravity. Yeah, if somebody sees something about altitude on that chart, please feel free to fill in the blanks on that. The heavier weight requires a longer takeoff roll, right? Because you need to generate more lift to carry that weight and to climb, and to basically turn the level of flight into a climb. You have to have excess lift to turn it into a climb. So your climb performance and ability to clear a tree getting out of ground effect will be affected if you're overweighted. Another problem that's kind of hidden is you can actually reduce your fuel economy because your tail's working really hard and you're inducing a lot more drag and you require more thrust. So you're going to burn through fuel more. But then you also do have it. What's that?
Plane's lighter.
Yeah, right. The plane becomes lighter. So then I make up for it, yeah. But you also have a reduced safety margin from stalling with a higher angle of attack, right? So all the other conditions, turns and approaches into the airport now have a reduced margin between your critical angle of attack. Pilot must know how much fuel can be loaded onto the aircraft without violating CG limits. That's that envelope chart we'll look at, as well as weight limits to conduct long or short flights with or without full complement of allowable passengers. Again, it's PAVE, right? This is PAVE. Again, so how do I load the plane so I can get make the mission successful with how far I want to go, and how much can I actually carry? How much useful load can I actually carry on this flight? Again, we talked about this. Aircraft loaded too far rearward may alternately climb and dive, becoming steeper with each oscillation. This is where I said, you might be able to, Stephanie's point, you might be able to overcome it, right? But the tail is never going to have enough command to fully pull out. And you might oscillate alternately between a climb and a dive. And then it could just get worse and worse, actually. And this is the controllability of the plane. It's to the same point. The other, this is the other one I didn't mention, is this flat spin thing. So imagine your CG's rearward, and if you take like an orange on a, I don't know, if you take a metal ball on a string or something, right, and you swing it around, right, it's pulling you. When it's swinging, it's actually pulling you. So imagine your CG's rearward and you're in a flat spin. That thing is just wanting to pull you out of trying to maintain directional control. So in a flat spin, that centrifugal force of the CG is actually preventing you from being able to have enough command of the rudder or directional control to recover from that flat spin, because the CG wants the plane to continue rotating. Does that make sense?
Yeah, so do you cut it? Is that what you do?
You cut the rope. Yeah. Yeah.
I mean, you just cut the engine, or you
Put
just
stuff out of the
you
back
less
Start unloading.
less the rest?
You're out.
You know what I mean?
I mean,
how would you pull out of that?
If you can muster up enough command of the rudder to overcome the flat spin, or if you can, I mean, you could try some crazy shit if you're desperate. Like, I'm just gonna dip the plane, and I don't,
I don't even know.
If you're
I mean,
going that
normal-
way, you might as well try, right?
Normally, you can recover from a spin by just slamming the elevator forward and getting as much airflow, over the wings, But in this case, I mean, think about it, you're getting spun around like teacups at Disneyland. You're probably not going to be able to.
Not the direction you want to be.
So, yeah, it's not a good place.
Yeah, I don't even know. Wow.
Zach asked, a typical training plane. Yeah, I mean, a passenger, what are you talking about? Like a 150-pound passenger? We've had 4 people in a 172 in a training session. So it's possible. It just depends on the weight of the people in the plane. So,
Typical people are
The-
150.
well, 170 is what they do. Yeah, that's the statute number they use. So, I'm just saying. Yeah. So the forward CG, not as detrimental, but it is for a tailwheel aircraft, because if you imagine the tailwheel kind of relies, on the CG being back here the way it sits right on the ground. So if it's here, it just, you might not actually be able to get the tail down on the ground. And steering, but for all planes, steering can be a little more difficult because it's relying on where the CG is on the ground controlling that plane. So if it's opposite of what you're expecting, that's why tail wheels are really, it's critical in a tail wheel. And I referred to page 544 in the fact for some reason, but I didn't leave myself any sort of hint as to why. It's page 554. Something's on there that's interesting. Here's that CG loading diagram in the book, talking about the center of lift relative to the CG and its position. So, and it's talking about how the tail has less command over restoring that stability. Man, that was a long chapter, but
There's some bullets right here that you're probably referring to.
yes, those bullets are written test bullets, probably. Yeah. I'm going to get through these additional topics quickly. I'm running out of time, but ice. Ice can be encountered any time of the year, requires visible moisture, and obviously a temperature that's conducive to ice. But the big point is snow, ice, and frost can change the characteristic of all the airfoils, the propeller, the wing, and the control surfaces. Now, snow and ice usually pretty obvious. Ice can be clear. You might not notice it, especially if it's dark out and you're pre-flighting a plane. Wintertime, I was doing training in Van Nuys, and we had frost on the wings in the morning. So it happens out here. Marcy and I had a 182 up here at Paso, and we just flew up, stayed overnight, and then wanted to leave in the morning, but the plane had frost all over it. So we had breakfast at Joe's and waited for the frost to melt off.
Well, you got some good food.
So, yeah. Yeah, so if you can remove frost with like glycol, and actually FBOs have a de-icing stuff they can spray on your plane, but we just waited it out. So so frost is really the key one. I mean, everything's like snow, ice. I mean, snow or ice can block the air intake for cooling your engine. We'll talk about air systems next time, but yeah, so frost is really the critical one because it disrupts the airflow over the wing. And then that reduces the critical angle of attack. So think about it, you're actually changing the design of the wing by having frost on it. So whatever your critical angle of attack was before, forget it. Now you're a test pilot. You have no idea what it is. So yeah, pretty much it. And your plane may not be able to take off. The book had this huge page on rate of turn, but then they also have radius of turn. So it's like, thank you. Like, which one are you talking about? It's really important if you're flying fast or large aircraft and you're trying to make a critical turn. You're not going to be tested on any of that. So.
Okay, good.
Why wouldn't
I
you
was
just
looking
fly
at the
up out of
formula.
that box canyon?
That's what I kept looking at.
mean, the diagram, they're just like, I mean, the edge is right there.
That diagram there.
1,000 feet of elevation, you're home.
I'll tell you what, so what can you do to reduce the radius of the turn? We talked about that before. So you could slow down the aircraft, right? But now you have a higher angle of attack, right, to maintain lift, right? But, so one of the maneuvers they teach you in a commercial license is this, climbing turn. And it's basically full power, but you're generating a huge amount of lift, but your ground speed is really slow, and your turn radius is really small and tight. And it's basically the box canyon escape maneuver, but it has a climb in it, right? So now you're actually reducing that distance you're traveling because you're climbing, right? So it kind of makes sense. Wing plane forms, there was a big page with a bunch of pictures of different wing shapes, but the basic idea is that, you can maintain the aspect ratio, which is the ratio of the wingspan to the chord, and manipulate the plan form to affect drag around it. This is an advanced topic. I don't think it's going to be on the private written. It was on the commercial written. And high-speed flight, I said open discussion, but we have no time. Anyone here hoping to fly super fast planes? Are you a billionaire, or do you work for a charter or an airline?
You said hope, you didn't see
Well, I would like
didn't
to
say
hope
we
maybe one
think it's
day
likely.
fly one, but you know, really
Well, this is how these are your two options, I guess. Or you have a buddy that doesn't mind you burning bunches of fuel in their really expensive.
Years left to get enough hours.
I got a buddy that's way up there.
Oh, there you go.
ACI in
That's awesome.
St. Louis, you know?
Hey, well, you never know.
Might happen.
You could get your time in. Key written points. Those 4 aerodynamic forces: the angle of attack, critical angle of attack. Yes, stalls, any airspeed. You know, and then the point I talked about, indicated airspeed, is indicating the airflow over the wings. So the indicated airspeed and the stall speed of the indicated airspeed is going to be the same because of the number of bits of air hitting your plane is an indication of the amount of airflow that's going over the wing. So if not the critical angle of attack, but the stall speed that's published, the low end of the stall speed, it's not going to matter if you're at different altitudes, I guess is what I'm trying to say there. The spin, one wing stalls more than the other. Ground effect, huge number of questions on it. Horizontal component of lift is what causes you to turn, and then the rudder is there to help the turn be coordinated. There is questions about stability. The torque effects that we talk about, they're greatest at a low speed. The question is like one question. It's they're greatest at a low speed and high angle of attack and high power. That's kind of what you got to remember there. The asymmetrical loading question, that's right, it is there, and it's because that descending blade takes a bigger bite. If you know that much, you'll pass the written question if it's there. Load factor, defining, reading, and applying that chart, and knowing what excess lift and excess load is, its effect on stalling and bank angle. So there's quite a few questions on load factor in the VG. If you want to go ahead and look at study unit 2, you could in the Gleim book, and it does talk about this stuff, but we haven't talked about the instruments or airplane systems yet. So that's it. Wow.
What the fuck?
Ran out of time. What the frack? So I have material for next week. You know, we're probably not going to get to instruments. So
You started?
do you guys want to spend a little more time here? 10 minutes? We can dig into this if you're okay with that.
Let's roll.
It's 8:30. Well, we technically go to 9, so.
Let's roll.
All right.
You don't need no questions and answers today.
No Q. Yeah, definitely no Q&A.
Do yourself.
Man.
I can't figure out what Ryan's asking, but from my understanding, the VG chart is only at a set speed, so the speed should have no reference to it, right?
Well, it was. It said weight and altitude. It says for a specific weight and altitude, and that's what the book said. At least that's what I think, but I'm not sure. Man, where the hell is that thing?
And then a certain speed it says too. Like the chart's just written for.
Is he talking about right here the maximum safe load factors?
Yeah, it's what chart is it? I have the label on there. There it is.
Each
Yeah.
aircraft has its own VG diagram that is valid at a certain weight and altitude.
Yeah. Yeah.
Yeah.
I mean, I'm not sure why altitude matters, and they don't even say, do they, in the book? Yeah. So there you go. Yeah. But yeah, that chart right there. All right. Oh, here we go. This one's shorter. You might be able to get through this one.
Let's power through it. Let's do this.
Ah! Duped. Duped. So duped. Well, yeah.
She's tired too.
Additional topics.
Oh, right there.
That's it. So, home. No. Slideshow from current slide. Yeah! Woohoo! Okay, this stuff we covered, a lot of it. Ailerons for banking and rolling. An up aileron decreases lift, right? An up aileron decreases lift, changes the camber, the chord line, lowering the wing about the CG, right? That's what they're gonna ask you on the written. What if I raise or lower the aileron, what is it gonna do to the wing and why does it do it? Elevator and stabilator for pitching, right? An up elevator decreases the lift of the horizontal stabilizer, right? Or the stabilator itself. Decreases the lift, which lowers the tail about the CG and raises the nose. And also we know that the tail is what balances our center of lift and center of gravity to maintain level flight. The rudder is a yawing device, and it left tail deflection swings the tail right, but that points the nose to the left. So pushing on the left rudder pedal turns you left. Secondary controls. So those are the primary controls. Every plane has them in some way. Secondary controls, flaps. So flap, again, is something that changes the camber of the wing, the chord line, and improving lift, and it helps at lower airspeeds. Now, it'll increase drag at higher airspeeds. So, but at a lower airspeed, you'll see on the airspeed indicator there's a white arc and there's a green arc. The white arc goes lower in airspeed than the green arc because the white arc indicates your stall speed with flaps. So you get a new coefficient of lift and coefficient of drag with flaps extended that allows you to fly slower and maintain flight. Leading edge devices mentioned on the written, but again, they change the camber of the wing and improve lift at lower airspeeds. Big ass commercial jets have them. You'll see these things shoot out of the front of the wing. Have you seen this?
Yeah.
Have you seen how big a big commercial jet's wings get during like landing? They're huge. The front comes out, and then the back goes out, and then it shoots down the side, and then there's like these spoiler things that fly out.
The military aircraft at the museum had the same kind
Yeah.
of thing going on. The prowlers did the aircraft
Yeah.
carrier.
It's crazy. So they become these big gliders at some point. And we talked about spoilers. Here's an actual airplane. So the yoke, right, controls pulling back on the yoke, lowers the wing and raises the nose, pushing forward opposite. You got the rudder that controls the yawing.
Did we talk about trim tabs?
Trim wheels.
Did I miss that?
No, we didn't. Trim, yes. And this is important too. The trim, right, reduces control forces needed to maintain. So imagine you're holding the elevator back to maintain level flight in some specific configuration or a climb. The trim wheel will let you trim that elevator out so that it holds that position without you needing to hold it with the yoke. So if you have a long climb, like sometimes the climbing to cruise can take 10 minutes. So you're going to be holding the yoke back for 10 minutes or trim it out. So you just need a little bit of pressure on the yoke to maintain that climb. Sometimes there's rudder trims too. The one in my plane is kind of funky. It actually pushes the rudder pedals. So you turn this little knob and it pushes the rudder pedals. Some planes will actually have a tab on the rudder. And then other planes have a tab that can only be set on the ground unless you're a wing walker and you can go back and adjust it. But there's like you'll see a little metal tab that sticks off the rudder that can be bent. The Cessnas will have that. So I guess if you fly the plane enough and you know how much to bend it, I don't know. But yeah.
We talked about it being useful for counteracting that engine rotational force or the
Yeah, that's
power plant force.
Yeah, that's a good for the slipstream. Yeah, I could see that. Yep. So the flight controls, right? Throttle is colored black usually. Propeller control is colored blue, and the mixture control is colored red. You enrichen the mixture by pushing it in and lean it by pushing out. You increase the propeller RPM by pushing in, reduce it by pulling out, and increase the throttle by pushing in and reduce the throttle by pulling out. My throttle quadrant looks more like the simulator here, so it's a bunch of levers, but the Cessnas have kind of this kind of look. They're kind of knobs that push in and pull out. Oh yeah, and then in this picture here, under the right yoke is the flap control. So it's usually like a little box control, and it has positions for the flaps. So there's like 0, 10, 20, 40 degrees, whatever. So there's like a little detent, and you can feel that position. Some planes can have a yoke or a flight stick. Most Cessnas, Beechcraft, and Pipers have a yoke. Earlier planes will have, like an earlier Piper will have a flight stick. And then some of the Beechcraft have this thing called a throw-over yoke. So it's actually one yoke, but it's connected in the middle, and you can throw it over you could throw it over to the other side.
Right.
Yeah, and then it's just mechanically, done that way, and it's thrown over. An aerobatic tailwheel planes will typically have a flight stick. I think it's just more convenient because they're a little bit tighter space. That's why. The Cirrus is a modern plane that actually has a flight stick, but it's mounted on near the side window on both sides. It's kind of it's like a joystick, a computer.
Video game.
Yeah, like a video game joystick. Yeah, it's kind of funny. The planes that will fly for flight training are to be mechanically connected. That means that there's a cable and a set of pulleys and push rods that are actually connected to each other. It's like a 19th century elevator, right? So very mechanical. And then there's force feedback, which is natural. So you'll feel the wind pushing on the control surfaces and wanting to push back. And again, that's why we have trim, right, to trim off that. But you'll feel the actual surface resisting movement. The trim devices, again, are to reduce that workload when you have that. I did one flight with my instructor, Patrick, who pushed on the right rudder pedal for the entire flight to see how well I could handle that. So that was interesting. Yeah. Very different. Well, I mean, the plane was like slipping or skidding the entire time practically, right? It was great when I wanted to turn, but, yeah. And when we landed, obviously, he didn't do it because that would have, the nose is directly connected to the rudder pedals and sheared it off. But so larger aircraft will have this hydraulic, this fly-by-wire. And it's simply because you don't have enough human strength to manipulate the control surface. So I worked on the flight computer for the Airbus 320, my first job. And they had a green and yellow system for that it was a backup system. The green system was the active one and the yellow was the backup. And these ones actually simulate that feedback, that natural feedback that you would feel in a mechanically connected system. So, but it's simulated, it's not real. Helicopters, way different book, different class. Here's the yoke, the joystick. Do you even call this a flight stick? I don't even know. They probably call it something else. The ailerons are for banking and rolling. Again, just think about the camber and the chord line, the angle of attack. Just think about that, and then you'll know what it means when you move it up or down, right? Changing the flight characteristic of the wing. One wing will have more induced drag than the other until you correct it with the rudder pedal, to bring them both around, have the airflow even. That's the adverse yaw. That drawing the nose to that wing, so that's why you get the slip when you enter the bank of the turn. The nose wants to pull outside of the turn. That's adverse yaw. Here's a picture showing adverse yaw. More lift, more drag. Pulls the nose to that side. Again, same thing. Think about the camber, the chord line, the AOA when the elevator's moved. Angle of attack. Changes the flight characteristic of the stabilizer. Again, just like on the wings. So you deflect down. So the stabilator is like, so the stabilator, one piece elevator and horizontal stabilizer all in one. And the angle of attack is the whole stabilizer's changed. But in a traditional elevator horizontal stabilizer, there's just a little flap at the back. On the stabilator, there's an anti-servo tab that looks like a trim tab, but it actually does move in the opposite direction of the stabilator. And what you're trimming is you're actually trimming the anti-servo tab differently instead of a trim tab. So it's a dual purpose trim device, and then it maintains that the lift over the elevator because the whole thing is rotating. The canard or canard, that's the one in the front. It looks like those fish with the thing in the front. It actually does create lift and holds the nose up. The Wright Flyer had one, and it was like a big boxy thing out in the front of the Wright Flyer. And then according to the book, it's supposed to result in less drag for certain amounts of lift. T-tail, and these are on the written test, or in some form maybe here. T-tail avoids most of the downwash. That tail is way up. Remember the wing downwash, the vortices and the downwash? Well, that tail is actually over top of the downwash, so it avoids it. And it's also out of the way of engine blasts, and it's clear water, so you'll see it that configuration used in some bush type planes as well. 8:47. How are we feeling? We can just go until 9. I mean, 9 was blocked out, so if you guys are okay with it, I'm cool with it.
However you feel.
Huh?
However you feel.
Oh, this is the easy stuff that.
Yeah.
There's a canard or canard or I gotta look it up, see how to say it.
And a top tail, T-tail.
Well, this is actually, it is a T-tail. Oh my gosh, yeah.
It's all of the
Boom!
things.
It's a bonus.
Maybe it's a stabilizer.
And they
too,
didn't
it's
even,
got everything.
right?
Solid one.
The one on the right is, if it's familiar to some of you, that's our airplane. That's a stabilator. So that's the anti-servo tab in the rear of that. We went out to see the plane, and it's pretty far away from getting put back together. Unfortunately.
Impressive.
I'm just so ready to go fly the damn thing. So the rudder. Do you see the Dutch rolls again?
Are you hungry?
Yeah. The vertical stabilizer is an airfoil, right? But it, moves the rudder right and left, creates sidewise aerodynamic forces. So it is an airfoil, and it creates sidewise forces. So the V-tail design, very popular in Bonanza, has no stabilizers, or does it? Well, they call them rudder vaders. Why not, right? So there's the rudder and the yoke are specially linked and mixed mechanically to control both of them as if it's normal. Because you don't want to go into this plane and have to learn a new type of control surface. So they actually blend the controls. But it's more susceptible to, guess what? Dutch roll.
So it's an experiment that's basically a failed experiment. It doesn't happen very often.
I don't know. I mean, I still see them around, and some people swear by them. So
Well, it's just the vintage planes. There's not a whole lot of new planes being built like this.
I haven't seen that used recently. I haven't. They might, but I mean, manufacturing costs. Maybe it's cheaper. There's less metal. I don't know. I don't know what the idea was.
Planes if they don't have a Dutch roll going on.
Dutch roll. That's right.
Sell planes that
Damn
don't roll.
Dutch roll.
Dang Dutch roll.
And, initially I thought Dutch roll was like a real good joint from like Amsterdam, but yeah,
I guess it could be
it might be too, right? Yeah.
Have the wedding cake.
They look good though, don't they? I just found that on whatever. So the control effectiveness, this is talked about in the written test too. So, as we've seen, all primary control surfaces are part of airfoils, right? And controls are most effective when the airflow is strong over them. So that's control effectiveness, right? Cirrus still uses the V-tail. That's true. That's where I thought I saw him. That's a good point. Is that the Unijet? Does the Vision Jet have a V-tail? It might. So when there's strong airflow over the controls, over the airfoils, the control surfaces, they're more effective. And the test talks about this. And pilots will talk about the command or the effectiveness of a control. So when I was doing my tail wheel training, he's like, yeah, you don't have as much command over the rudder when you're coming down for the landing, because you don't have enough airflow over it. Yep, Vision Jet. I knew it. That's right. That thing I don't know. It's cool, but it's got a jet in the back. And it has a V-tail, so the jet blast doesn't go through a stabilizer. Yeah, that makes sense. Yeah, so it's got a V-tail, so the jet blast doesn't go through the stabilizer. Yeah.
They just do everything weird and serious. They got the weird joysticks. They got the weird.
Yeah, they're innovators. That's what.
Overpaid design staff.
Maybe. People love the Cirruses. I don't know. So at slower speeds, the controls are less effective. So as you're rolling out, and again, like I said, when you have a strong headwind on a landing, you want to have more control over the aircraft. So you'll tend to fly in a little bit faster because your ground speed's reduced anyhow, but you have more command over the aircraft at a higher airspeed. Secondary flight controls. So flaps, that trailing edge device, increases lift and induced drag for any angle of attack, right? So you'll slow down the plane. Sometimes you want the plane to actually slow down because you're coming in too fast or whatever. You need to slow the plane down. You don't really care about the lift yet. So you can actually use the flap as a way to reduce your airspeed, but then you also get the benefit of an additional lift. And then that means you can go slower. This is the written question right here. The slotted flap is the most popular since they increase lift more than plain or split flaps. So, and you consider yourself lucky because the written had like all, those like 5 or 6 different flaps. They used to ask you about, they had like 8 questions that would ask you about each of them. Now they've decided they only want to ask you about the slotted flap. So. We talked about spoilers. I could talk about them again, but yeah, they reduce lift and increase drag. It's mainly to reduce the airspeed. Gliders will have them too because gliders don't have an engine, so you have to have ways of, changing airspeed. The trim systems, like I said, relieve control pressure. There's the trim tabs and the servo tabs. There's the ground adjustable tabs. We talked about that. Elevators and sometimes rudders have trim. Written test key point. Stabulator, we talked about that. And canard. Know what a rudder is. Know what control effectiveness means. Know about that slotted flap. Basically, all the points I mentioned about trim systems are on there. And trim tabs move in the opposite direction of the elevator. Trim tab up moves the elevator down, which pitches the plane up. So the idea that it's opposite and yeah. So you just got to think about all the surfaces and there's a picture in the book, I think, that shows like the elevator getting pushed down, but the trim tab's up, and it does, yeah.
It's probably because it's the most popular flap, this slotted flap of today.
That's maybe that, that's why it's on the, yeah. Because I'm like, why are they talking about the Fowler flap and all these other ones? That slotted flap's the only thing I've ever seen. My plane has it, the Cessnas have it. Yeah, but they show them. So this will be next week. This is what we're reading next week. I'm going to go ahead and skip to the end here because you can start looking at Study Unit 1 in the Gleim book. Man. And Chapter 7's big. Don't get me wrong. What do you freaking current slide? There we go. Bam. Knowledge test, Study Unit 1. We've covered all that information, so you can go ahead and go through that. Here's the layout. Aircraft systems is going to apparently be done along with flight instruments next week. When you read Chapter 7, you can exclude superchargers, turbochargers, turbine engines. I'm sure Ryan will still read it. He likes that, so you're going to read it too. Yeah, okay.
It's Motorhead kind of stuff.
It is Motorhead, but no obligation. Pressurized aircraft, oxygen systems, anti-ice, and de-icing. Do not worry about reading those sections. Chapter 8, flight instruments. That one isn't terrible. Chapter 8, flight instruments, looks like it's 27 pages long.
Accelerated course guide.
That's what I said, and I'm falling behind now because look at me, I can't even keep up with my own schedule. Well, at least I have slides for all of Chapter 7 ready, so yeah. So there you go. So yeah, flight instruments, and then like I said, we'll do a progress check after week 3. I'll come up with some kind of quiz or something.
Prize.
Yeah, and then we'll just do,
Ground School Jeopardy.
Yeah, well, a prize? Did you say a prize? It's going to be, I'll have to do Amazon gift cards or something because it's all the people that are, yeah.
You don't have to worry about it. I'm right here.
Gift cards.
There you go.
We can go to the Barrel House still.
That's all right. We can just sneak over to Barrel House. Yeah, so flight instruments, and then we'll do a progress check. Like I said, if you guys are serious about the written, now I need to know for this progress check. So by week 3, let me know who's going to take the written test. All those you online too, if you're going to do it. If you're just following the class, I don't need to give you a quiz. You're certainly welcome to do the quiz if you want, but no obligation. But if you are going on to the written, you have to do the quiz.
We're gonna go through all this Bernoulli material.
Well, some people just want.
Brian found a website. He's back on the main discussion.
Oh, is he? Oh, okay.
About the VG speed graph.
Yeah.
It says air pressure affects the graph, which is why altitude is part of the.
Oh, so it's just pressure, air density, really, right?
Mm-hmm.
Yeah. I mean, that would make sense. So.
Yeah.
Yeah.
Good job, Brian.
Good job. I will give you a smiley face. Where's one here?
What's the cowboy hat mean?
I don't know. Giddy up, giddy up.
Giddy up, cowboy.
Getting cowboy hats.
You keep getting cowboy. I gave you a cowboy
I
hat.
didn't give you a cowboy
I said
hat.
giddy up. All right. Well, cool guys. We got through. I'm glad we got through that extra section. Honestly, we'd be really far behind if we didn't do that. So
No, it's free.
yeah. Aircraft systems and flight instruments next week. This right here. I'll just paste those exclusions out. There. It wasn't a question, so I posted it. That's good. Fair enough.
Directing.
Oh, wow.
Golden rules.
Whew, see how rosy my face is from all that talking and these lights in there? It is, the brain. Actually, it's good. It's a good look for me. I like it.
You need a beer.
I do need a beer. Well, I totally need a beer. All right. Thanks again, everyone. I will make this available online as soon as possible. I'll try to put little markers, chapter markers in it too, so you can find stuff quickly.
Cool.
I did that in the last one. If you go to the comment section, there's like a hyperlink that'll take you to a specific
Okay.
section in it. So I'll try to at least break it up that way. And then we'll see you next week at 6 o'clock.
Having that thing. That thing is heavy.
All the books.
Thanks, everyone.
What do you need?
All the books. And some.